All gas turbine engines use high-energy igniter units, or HEIUs, for engine starting. We'll investigate the intricacies of the high-energy igniter unit later. All gas turbine engines have a dual ignition system fitted, which means that they have two high-energy igniter units. The high-energy igniter units each feed a separate igniter plug. High-energy ignition systems have an output of approximately 12 joules. It may sometimes be necessary, to help prevent engine flameout, to have the ignition system selected in circumstances other than engine starting. For instance, during takeoff from contaminated runways, or flight through heavy precipitation. The use of the high-energy ignition system on these occasions will cause the igniter plug to erode so quickly that it will shorten its working life dramatically. To minimize erosion of the igniter plugs, some aircraft engines are fitted with a combination ignition system, which includes a low-energy, 3 to 6 joules, continuous selection, as well as the high-energy, 6 to 12 joules, starting selection. Continuous ignition, which energizes the low-energy mode of the igniters, is usually activated by selection of the appropriate switch on the engine start panel. The starting ignition system is activated when the engine start sequence is initiated, either automatically or by the operation of the high-pressure fuel cock, start lever, or fuel and ignition switch. The igniters are automatically deactivated at some point after self-sustaining speed, usually by the operation of a speed switch incorporated in the high-pressure compressor RPM indicator system. Some aircraft have an automatic ignition system. If an aircraft stall is detected, the aircraft stall warning system will automatically select the continuous ignition system. The high-energy ignition unit works on the principle of charging up a very large capacitor and then discharging it across the face of an igniter plug. The size of the capacitor makes it a potentially lethal device, and several safety factors have to be built into the high-energy ignition unit so that it conforms to safety regulations. This diagram shows the high-energy ignition unit mounted on the side of an engine and also the position of the igniter within the combustion chamber. The circuit shown here illustrates all of the components within a high-energy ignition unit, which is supplied by 28 volts direct current. With the supply connected, the primary coil and the trembler mechanism are fed with 28 volts direct current. The trembler mechanism works on the same principle as that of an electric bell. By doing so, it causes the primary coil input to become a sawtooth waveform. This sawtooth waveform is a very crude form of alternating current. Because we've generated alternating current, we can use a transformer to boost the voltage in the primary coil to 25,000 volts in its secondary coil. The 25,000 volts alternating current is changed back to direct current in the rectifiers. The direct current commences charging the reservoir capacitor. As the value of the charge in the reservoir capacitor builds up, it eventually reaches a level that causes a spark to jump the discharge gap. The discharge gap exists within an evacuated tube. The fact that the tube is evacuated means that changing conditions of humidity and altitude will have no effect on the voltage required to jump the gap within the tube. Consequently, the power of the spark at the igniter plug will be constant, regardless of ambient conditions. The electrical energy which has crossed the discharge gap has then to flow through the choke. The choke acts as an inductance and slows down the current flow. Slowing the rate of current flow makes the duration of the spark longer. The energy then passes to the igniter in the combustion chamber. If the unit has to be removed from the engine for servicing, any charge which may remain in the capacitor, even after the electrical power to the unit has been disconnected, could be lethal to anyone touching the casing of the high-energy igniter unit. The discharge resistors act as a safety device, by allowing energy trapped in the capacitor to leak away to Earth once the supply has been removed. The safety resistors act as a kind of safety valve if the igniter plug becomes disconnected. If the igniter plug did become disconnected, energy would continue to build up in the capacitor. The build-up of energy in the capacitor would eventually cause it to explode. To safeguard against a potentially engine-disabling explosion, the safety resistors allow energy in excess of the normal level to flow through them in an attempt to balance the charge on the plates of the capacitor. The normal spark output rate of the high-energy ignition unit is between 60 to 100 sparks per minute. However, the production of sparks is completely random, and if relight is selected with the aircraft on the ground, anyone listening at the jet pipe before engine start should hear an unsynchronized beat if both units on the engine are working correctly. As well as the direct current high-energy ignition unit, there are transistorized high-energy ignition devices. For aircraft which have an alternating current electrical system, there are units which will work on that supply. There are two types of igniter plug. The older of these two types works in a similar manner to that of the piston engine spark plug, but it has a much bigger spark gap. The potential required to jump this gap is approximately 25,000 volts. This extremely high potential requires very good insulation standards, both within the unit and in the cabling to the igniter. A more modern version of the igniter plug is the surface discharge igniter plug shown here. The end of the insulator of the surface discharge igniter plug is formed from a semiconductor material. The semiconductor material allows an electrical leakage to occur between the hot electrode to the body of the igniter. The electrical leakage ionizes the surface of the semiconductor material, which provides a relatively low resistance path for the energy stored in the capacitor. The discharge takes the form of a high-intensity flashover from the hot electrode to the body of the igniter, which only requires approximately 2,000 volts. This concludes the lesson on ignition systems. There are three basic requirements which must be satisfied before we can start a gas turbine engine. They are that the compressor turbine assembly must be rotated to get air into the combustion chambers, that fuel must be provided in the combustion chambers, that ignition must also be provided in the combustion chambers to start the air-fuel mixture burning. Supplementary to these basic prerequisites for engine starting are two other requirements which satisfy servicing essentials. The necessity to motor over the engine with no igniters operating. This is sometimes called a blowout or motoring over cycle. The necessity to motor over the engine usually only occurs when there's been a failure to start. A failure to start is sometimes called a wet start. The need for the igniters to be operated independent of the start cycle. There are several methods of obtaining engine rotation upon engine start. The most common methods of rotating the high-pressure compressor on modern civil aircraft are the electric starter motor, the air starter motor. Any engine starter system will have a duty cycle. The duty cycle is the maximum time that the starter motor is allowed to be energized. The duty cycle may have to be followed by a cooling down period before the starter motor can be re-energized. The electric starter motor was the original means of starting a gas turbine engine, and is still used in smaller executive jets and helicopters. However, it's fallen out of favour in larger and more modern engines because of its weight. This picture shows a dart engine where the electric starter motor is fixed in front of the compressor casing. The electric starter motor can, however, be attached to the engine accessory gearbox. In the latter circumstance, the starter drives the compressor through the gearbox. Rapidly becoming more popular on smaller engines is the starter-generator combination, which, because of its dual purpose, has a greater usefulness-to-weight ratio. The air starter motor is possibly the most popular starting system on large gas turbine engines. It's light, simple to use, and very economical, insofar as it utilizes low-pressure air as its power source. The air starter motor is attached to the accessory gearbox of the engine. The sources of air available for engine start, in order of preference, are the Aircraft Auxiliary Power Unit, or APU. Use of an APU does not cost the airline anything, so it definitely will be the favourite method of supplying air for engine starting. The Ground Start Unit. If a ground start unit is required, perhaps because of APU unserviceability, the airline will have to pay for its use. This is understandably not too popular with the airlines. A crossbleed start, where air from an already started engine is used. A crossbleed start doesn't cost the airline anything, but it does require that the engine that supplies the air has power applied to it. In the crowded environment of the ramp, applying power to an engine carries obvious risks, and some airport authorities are reluctant to give permission to the pilot to carry out this type of operation. Air from one of these sources is fed through an electrically controlled air start valve to the starter motor's air inlet, where it's used to turn the turbine rotor. The air is subsequently exhausted to atmosphere. The turbine rotor turns the reduction gear, which rotates the engine high-pressure compressor shaft through a ratchet clutch arrangement, which is designed to prevent the starter motor being driven by the engine after engine start. The danger, should this happen, is that the starter motor will rotate at a speed sufficient to cause it to break up due to centrifugal force. A flyweight cutout switch may also be included in the control circuit of the air start valve. This shuts off the starting air supply by de-energizing the air start valve. This device will automatically terminate the engine start cycle when the engine has reached a speed slightly in excess of self-sustaining speed. We'll explain the starting sequence of a generic twin-spool medium bypass gas turbine engine using two methods. Firstly, we'll go through the sequence using the engine controls to demonstrate the required actions, and the engine instruments and a generic air starting supply layout to illustrate the results of those actions. The second method will utilize a graphical representation of the relationship between RPM and EGT during a normal engine start sequence. This very simplified air start supply layout for a twin-engined aircraft shows each engine fitted with an air starter motor. When engine start is selected, each starter motor will be supplied with low-pressure, high-volume air from either the APU, the ground start unit, or another engine which is already running and capable of supplying air. On this particular start, we'll utilize the aircraft's APU to supply air. The aircraft's normal bleed air system ducting is utilized to pass the air to the starter motor. Non-return valves at the low-pressure and high-pressure engine bleed positions prevent air leaking back into the engine compressor during engine start. The engine instruments which require the most attention during the engine start sequence are the exhaust gas temperature gauge, EGT, and the high-pressure compressor rotational speed gauge, N2. These two parameters must be monitored closely to ascertain whether or not the start cycle is proceeding safely. Other instruments that should be monitored during the start are fuel flow, engine oil pressure, low-pressure compressor rotational speed, otherwise known as N1, system duct pressure, and the start valve open light. Normally the number 2 engine will be started first. For the first start of the day, right ignition is selected, and the number 2 engine start switch is selected to ground, which is the ground start position. The selection of ground opens the APU control valve and the number 2 engine air start valve. To indicate that air is getting to the starter motor, the start valve open light above the engine instruments illuminates. The starter motor turns the high-pressure compressor, which we can note by checking the N2 reading. This is an appropriate time to start timing the starter motor duty cycle. As the N2 increases, the oil pumps will produce sufficient pressure to extinguish the low oil pressure caption. At 24% N2, the number 2 engine start lever should be moved to the idle detent. This supplies fuel to the engine and initiates the AC ignition system. The operator should keep his hand on the start lever in case of an engine starting fault, in which case he should immediately close the start lever. On most twin or triple spool engines, it's advisable to ensure that the other spools are rotating in the correct direction, especially if starting engines with a tailwind. A short time after the start lever has been opened, the engine should light up. This is indicated by an increase in the EGT and an increased rate of acceleration of N2. At approximately 46% N2, the start switch will automatically move to the off position, and the start valve open light will extinguish. The starter duty cycle is now complete, and the N2 should continue to increase to the ground idle value of between 58 to 62%. When the engine RPM has stabilized at ground idle, the fuel control and, if appropriate, the ignition switch can be released and the after-start checks carried out. We'll now use this graph, together with the simplified air start supply layout, as the second method of demonstrating how the exhaust gas temperature and high-pressure compressor RPM relate to each other during a normal engine start cycle. As before, we'll again use the APU as the source of starting air. Upon engine start selection, air is fed from the ducting to the starter motor via the air start valve. The compressor accelerates under the influence of the starter motor and starts to force air through the combustion chambers. Initially, fuel and ignition are not supplied. Each type of engine will have a specific high-pressure compressor RPM when both the fuel supply and the ignition should be activated. Fuel and ignition are, in this case, selected by moving the start lever to the idle detent when N1 reaches 24%. Engine light-up is indicated by an increase in exhaust gas temperature and must occur within a specified time. 20 seconds is typical. The initial increase in EGT is quite sharp because of the fact that as combustion does not occur immediately after ignition is selected, there is an initial build-up of fuel in the combustion chamber. Once this fuel does ignite, it tends to overpower the cooling effect of air being fed from the compressor. Once the excess fuel is burnt off, however, and the fuel-air mixture becomes more balanced, the increase in EGT steadies. The gas which is being produced in the combustion chambers now adds impetus to the turbine blades, which eases the task of the starter motor, and the engine continues to accelerate. The accelerating engine drives the high-pressure fuel pumps faster and faster, until they eventually manage to drive sufficient fuel through the fuel control unit, which enables it to supply the idle level of fuel flow to the burners. However, the compressor is not yet running at idle RPM, so once again there is too much fuel being supplied to the combustion chambers, and not enough cooling air. Evidence of this is given by the second steep rise in the EGT. Eventually the engine accelerates to self-sustaining speed, which is approximately 36% N2. The starter motor is not, however, deselected at this point. It's kept operating to assist the engine to accelerate a little more. This gives the engine a better chance of reaching idle RPM without exceeding its limiting EGT. The igniters and the air supplied to the starter motor will be cancelled automatically by an N2 speed switch at 40% N2. As engine acceleration continues towards this point, the EGT peaks. But as the airflow and the fuel flow become balanced at their idle RPM values, the EGT drops to the value appropriate to idle RPM. Ground idle RPM is approximately 60% N2 and 25% N1. A motoring overcycle, sometimes called a blowout cycle, may be required if there has been an unsuccessful attempt to start, as appears to be the case here. Any fuel which remains in the engine after an unsuccessful attempt to start has to be evaporated, blown out, or allowed to drain away before another attempt can be made to start the engine. Carrying out a blowout cycle should prevent torching, which is a phenomenon caused by excess fuel, which remains in the engine, catching fire in a subsequent attempt to start. To achieve a blowout cycle, the starter motor is activated without the selection of either fuel or the ignition system. When it's used for a blowout cycle, a typical air turbine starter motor has a duty cycle of 2 minutes on, followed by a 5-minute cooling down period. Always check the manual to determine the exact duty cycle of the starter motor that your engine has fitted. In the event of an engine flaming out while the aircraft is airborne, it may only be necessary to initiate the fuel flow and activate the ignition system without operating the starter motor to achieve a relight. The starter motor should not be required to rotate the engine in these circumstances because the engine should already be windmilling. On this aircraft, if both ignition systems are selected and the appropriate engine selector moved to the flight position, a relight should be achieved if the failed engine's start lever is moved to the idle detent. Evidence that an attempt to relight has been successful will be obtained from the EGT and RPM gauges. A rise in the value of either of these shows that a relight has occurred. It's really only possible to determine that a hot start is happening by comparing its indications to those of a normal start. The EGT may initially rise as normal, but then a rapid rise towards the engine's EGT limit caused by a hot start will become apparent a few seconds after light-up. In many cases, the only chance of stopping the temperature limit being exceeded lies in having the ability to switch off that engine's fuel supply as quickly as possible. Waiting for instructions or discussing the indications will almost certainly cost you or your company the price of a new engine. Hence the advice to keep your hand on the fuel supply control. If the EGT exceeds the limit by only 1 degree, the engine is to be considered unserviceable. The reasons for a hot start lie almost entirely in having either too much fuel or not enough air to cool the gases through the turbine. A surplus of fuel can be caused by a variety of reasons, such as the throttles either not being set to idle during the pre-flight check or being knocked away from the idle position after the pre-flight check. A shortage of sufficient cooling air can be caused by the engine not rotating fast enough, maybe because the duct pressure is too low to drive the starter motor at the required speed. Slow engine rotation could also be caused because ice accretion within the compressor annulus has caused a partial seizure of the compressor. A hot start can also be caused by the aircraft being positioned, perhaps for its second start of the day, with the wind going up the jet pipe, as opposed to the ideal situation when the wind would be going into the intake. The tailwind will make the job of the starter motor more difficult, and it will have more trouble pushing sufficient air through the engine quickly enough to keep the core temperature within limits. The residual heat that remains in the engine after shutdown will exacerbate the problem. The failure of the gas turbine engine to start, more commonly known as the wet start, is indicated by its EGT not rising and its RPM stabilizing at the maximum that the starter motor can achieve. If the engine fails to light up within the required time limit which is usually about 20 seconds, then the ignition supply should be deselected and the fuel supply shut off. However, it may be some time before it's realized that there is a problem, and that the problem is a wet start. Starting malfunctions on gas turbine engines are rare and always come as a surprise, except in the flight simulator, where they tend to become the norm. Thus, there can be a long period during which fuel is being pumped into the engine before the problem becomes apparent. Throughout that period, the combustion chambers and exhaust system are becoming saturated with fuel. The fact that fuel is entering the engine can be confirmed by a glance at the fuel flow meter indication at the instant of moving the start valve to the idle detent. Two dangers exist if this fuel is ignited. Firstly, it will cause a very large jet of flame to issue from the exhaust system, the phenomenon called torching. And secondly, the rise of EGT may well be uncontrollable and could exceed its limitation. To prevent torching and excessive EGT, before attempting a second start, a motoring over or blowout cycle must be carried out. So, immediately the wet start is diagnosed, do not terminate the start cycle. Instead, promptly shut off the high-pressure fuel supply and deselect ignition, and then allow the starter to continue to turn the compressor for the time remaining in that start cycle before attempting a blowout cycle. These actions will allow the compressor to start blowing out any fuel from the engine even before you carry out the blowout cycle proper. The obvious cause of a gas turbine engine failing to start is a lack of ignition. The ignition units are generally quite reliable. However, they do sometimes fail. It can be difficult to determine from the cockpit of a large airliner whether or not you have sparks in the engine. On some aircraft there is a clue which is given by the very nature of the igniter units themselves. Really high energy outputs will sometimes make themselves heard on the intercom system as a background buzz. If you can hear that noise on the intercom during the start cycle, or when the relight facility is selected, then it's probable that the igniter units are operating. Alternatively, if your starter crew trust you, and if it's safe for them to do so, you could direct them to the rear of the engine, and, having selected relight, ask them to listen for the asynchronous ticking noise which two high-energy igniters make when they're feeding spark to two serviceable igniter plugs. Another cause of a gas turbine engine failing to start could be a lack of fuel, but this is fairly unlikely to occur on an engine that was working perfectly when it was shut down. A check of the fuel flow meter when the start lever is operated will give you ample evidence of whether fuel is being fed to the engine or not. The indications of a hung start are the EGT being higher than would be expected for the RPM at which the engine has stabilized, and the RPM being lower than the engine's self-sustaining speed. The high EGT is, however, usually not greater than the limit. Nevertheless, maintaining the engine in this state will do it no good at all, and could do it a great deal of harm. If a hung start is indicated, then the high-pressure fuel supply must be shut off and the problem investigated. The usual cause of a hung start is that there is not sufficient airflow through the engine to support efficient combustion. There could be a number of reasons for this insufficient airflow. For instance, if you're at a high-altitude airfield and you're attempting to start an engine which has a contaminated compressor, that compressor will choose this time to make its inefficiency felt. On the other hand, insufficient motive power being applied to the starter motor will prevent it from being able to rotate the compressor fast enough to push the required amount of air through the engine. This means that the gases generated in the combustion chambers will not have sufficient power to assist the starter motor in accelerating the engine beyond self-sustaining speed. Thus, once the starter motor cycle has finished, the engine RPM remains stable below the figure that will enable it to accelerate up to ground idle speed. Engine rundown time, or spool down time, is the time taken for the engine to stop after the high-pressure fuel supply is shut off. When the engines are shut down after flight, a mental note should be taken of the rundown time of each engine, and a comparison made between those times. Any engine with a rundown time appreciably less than the others should be noted. A short rundown time may be indicative of an impending malfunction. The entire system which stores, carries and controls the fuel supply for the engines can be divided into two sections: the airframe fuel system and the engine fuel system. Here we'll look specifically at the engine fuel system, which receives the low-pressure fuel supply from the aircraft fuel tanks, which are part of the airframe fuel system. The engine fuel system increases the fuel pressure to a value that the fuel nozzles in the combustion chamber can use, and then controls the volume of fuel into the engine so that it conforms to the engine's requirements. The engine fuel system consists of a number of components which we'll now describe in more detail. The booster pumps, which are situated in the wing and centre tanks of the airframe fuel system, pass fuel through non-return valves to the engine via the low-pressure fuel cock. The low-pressure fuel cock is electrically operated. It can be shut automatically if the engine fire control handle is activated. If a component of the fuel system needs to be removed, for whatever purposes, the low-pressure fuel cock can be used to shut off the supply of fuel to the engine to facilitate the removal. If the high-pressure fuel cock cannot be used to shut down the engine for whatever reason, as an alternative, the low-pressure fuel cock can be used to stop the engine. However, using the low-pressure fuel cock to shut down the engine instead of the high-pressure fuel cock will mean that the engine will take much longer to shut down. This is because the pipeline between the low-pressure fuel cock and the engine contains a considerable amount of fuel, which will maintain the supply to the burners for some time, whereas in the case of the high-pressure fuel cock, very little fuel is contained in the pipeline between it and the combustion chambers. After it's passed through the low-pressure fuel cock, the fuel then enters the engine fuel system and is delivered to the low-pressure fuel pump. The low-pressure fuel pump is sometimes called the backing pump because it will attempt to back up the fuel supply to the engine in the event of failure of both of the booster pumps in the wing tanks. The low-pressure fuel pump is used to supply positive fuel pressure directly to the high-pressure pump. By maintaining a positive pressure, the low-pressure pump minimizes the chance of cavitation occurring at the inlet of the high-pressure pump. The low-pressure fuel pump is driven by the engine's accessory gearbox, which itself is driven by the high-pressure compressor shaft. A fuel-cooled oil cooler is fitted in the majority of gas turbine engine installations. The oil cooler serves the double purpose of cooling the oil and also heating the fuel. By raising the temperature of the fuel, the oil cooler eliminates the formation of ice crystals, which may block components downstream in the fuel system. The oil feed line to the fuel-cooled oil cooler incorporates a pressure-maintaining valve. This valve keeps the oil pressure in the cooler higher than the fuel pressure. If the oil cooler does develop an internal leak, then the fact that the oil pressure is higher than the fuel pressure will ensure that the oil leaks into the fuel system, rather than the fuel leaking into the oil system, which could be very dangerous. The fuel heater assists in the warming of the fuel, and thus the elimination of ice crystals. The fuel heater, working in conjunction with the fuel-cooled oil cooler, uses compressed bleed air to warm the fuel to automatically maintain a predetermined fuel temperature. The automatic temperature control can be achieved by the action of a Werner-Therm thermal actuator. The thermal actuator incorporates a material which is sensitive to temperature change. This is used to open or close a valve, which regulates the entry of hot air into the fuel heater from the engine compressor. The low-pressure fuel filter is the first line of defense, protecting the delicate control components within the high-pressure fuel pump and the fuel control unit from the effects of dirt or contamination. The low-pressure filter is usually a replaceable paper filter element, which is capable of filtering out particles larger than 50 to 100 microns. The flow meter measures the instantaneous fuel flow in gallons per hour, kilograms per hour, or pounds per hour. The flow meter may also include an integrating system, which can add the total amount of fuel used. There are basically two types of flow meter in use on large jet aircraft. They are the vane type and the mass flow measuring type. The vane type of fuel flow meter, which is fitted to older aircraft systems, is designed to measure volume of flow. The flow meter consists of a vane which is moved against the force of a restraining spring by the volume of fuel flowing past it. This system is not too accurate. The mass flow type of instrument can be accurate to within plus or minus 1%. Fuel flowing through the instrument rotates both a drum and a spring-mounted impeller, which have magnets fixed to them. Movement of the magnets is sensed by pickup coils, which translate the difference in angular displacement between the magnets into a mass flow rate. The fuel temperature is sensed as the fuel leaves the fuel heater. Fuel temperature is indicated on the flight deck to allow system monitoring. The fuel pressure is sensed as the fuel leaves the low-pressure fuel filter. Fuel low pressure may be indicated by either an LP fuel warning light or the activation of warnings on the ICAS or ECAM, depending on aircraft type. The high-pressure fuel pump is fitted to and driven by the engine accessory gearbox. The engine accessory gearbox itself is driven by the high-pressure compressor shaft. The high-pressure fuel pump, illustrated, is representative of one type of pump employed. It's a plunger-type pump. It can be used as a single unit, if the volume of fuel required is not too great, but in larger engines 2 units can be driven together to supply a greater fuel flow. Several plungers are fitted on a rotor assembly. The plungers are rotated against a stationary cam plate, which causes them to reciprocate within the bores that contain them on the rotor assembly. The distance that the plungers move during this reciprocating action is dictated by the angle of inclination of the cam plate. Here we see the cam plate angled so that the plungers stay in the same position in their bores as the rotor drives them round. Now the cam plate angle is such that the springs force the plungers to their maximum stroke when they are at the top of the cam plate, sucking fuel into the bores. And the cam plate forces the plungers to their minimum stroke when they are at the bottom of the cam plate, forcing fuel under pressure to the outlet of the pump. The angle of inclination of the cam plate is controlled by a servo piston, which itself is controlled from the fuel control unit. Most fuel systems incorporate a fuel filter into the output of the high-pressure fuel pump to prevent very fine particles entering the extremely small passageways inside the fuel control unit. The fuel filter is composed of a number of wire mesh screen discs. The spur gear type fuel pump is simpler and lighter in construction than the plunger type fuel pump, and like the plunger type pump, the spur gear type pump is driven by the accessory gearbox. The output of the spur gear type pump is directly proportional to its rotational speed. The fuel control unit controls the fuel flow to the burners for every thrust setting. There are 2 types of hydromechanical fuel control systems still used on gas turbine engines. They are the pressure control system and the proportional flow control system. The proportional flow control system is the more popular of the two types because it is more compact than the pressure control system, and it's not sensitive to the effect of flow variations that occur downstream of the throttle. The proportional flow control system is the type we'll use to describe the individual parts of a fuel control unit. Various devices within the fuel control unit are used to adjust the fuel flow to cater for variations in air intake pressure, engine acceleration control, exhaust gas temperature, RPM limiting, and compressor delivery pressure. Variations in air intake, or P1 pressure, require that the fuel flow to the burners is adjusted so that a fixed RPM is maintained for a selected throttle position at all altitudes and airspeeds. This is achieved by the expansion or contraction of a capsule influenced by P1 pressure, which in turn modifies the fuel flow to suit the new conditions. This capsule, known as the barometric pressure capsule, is incorporated in an altitude sensing unit within the fuel control unit. It's necessary to increase the fuel flow to the engine to make it accelerate. However, too rapid an increase of fuel flow into the engine can cause compressor stall and surge. To regulate the fuel flow under conditions of engine acceleration, an acceleration control unit is fitted within the fuel control unit. The acceleration control unit receives information regarding engine intake pressure, P1, and compressor delivery pressure, P3 for a two-spool engine, and uses this information to adjust a fuel metering plunger. The fuel metering plunger effectively acts as a second throttle valve in series with the main throttle, and it regulates the fuel flow to achieve the fastest engine acceleration without causing stall or surge. Exhaust gas temperature is probably the most important parameter in a gas turbine engine. To obtain maximum efficiency, the engine must be run at the highest possible temperature in the turbine without melting the materials from which it's made. To achieve these conditions and yet still allow the engine to be a practical, user-friendly unit, automatic monitoring of the exhaust gas temperature is combined with a top temperature control unit. The top temperature control facility allows the pilot to select full power at any time without risking a meltdown in the turbine assembly. Thermocouple probes are positioned in the gas stream, either within the turbine assembly or close after it. The output of these thermocouples is used to measure the temperature at the rear of the engine. This output is passed both to the cockpit instrumentation and to a temperature control signal amplifier. The electrical output of this amplifier drives the solenoid, which indirectly controls the fuel flow to the engine. The ability of the compressor to withstand internal pressure is limited by the strength of the materials from which its casing is made. If the compressor casing is subjected to pressures greater than its design maximum, it will break, with probably catastrophic consequences. To prevent compressor casing failure, the fuel control unit incorporates a power limiter device. The power limiter receives signals of both intake pressure, P1, and compressor delivery pressure, P3. The ratio of P3 pressure to P1 pressure can be found by combining these signals. A system of capsules and levers controls the fuel flow to the engine so that a maximum pressure ratio is never exceeded, and thus the integrity of the compressor casing is retained. If excessive centrifugal force is to be prevented from destroying the compressor spools, their maximum rotational speeds must be limited. There are basically two methods of achieving this compressor rotational speed limitation. The first method of controlling the rotational speed of a compressor, usually the low-pressure compressor, depends on an electrical signal proportional to the speed of the compressor shaft. A tachogenerator or electronic speed sensor, which is driven by the appropriate shaft, sends signals to an amplifier. If the output of the tachogenerator approaches a predetermined maximum level, the fuel flow will be adjusted to prevent the maximum RPM being exceeded. The second method of controlling the rotational speed of a compressor is normally used to control the speed of rotation of the high-pressure compressor shaft. This high-pressure compressor shaft drives the accessory gearbox, which in turn drives, among other things, the high-pressure fuel pumps. Fitted within the high-pressure fuel pump is a hydromechanical governor. The hydromechanical governor uses hydraulic pressure as its controlling parameter. The hydraulic pressure, which is generated inside the pump by the rotation of the moving parts, is proportional to engine speed. As engine speed, and thus hydraulic pressure, builds, it acts on a diaphragm. Movement of the diaphragm opens valves which bleed off some of the servo piston pressure, which reduces the high-pressure fuel pump cam plate angle. This reduces the high-pressure fuel pump output and attenuates the fuel flow to the burners. The high-pressure fuel cock, sometimes called the high-pressure fuel shutoff valve, controls the flow of fuel between the fuel control unit and the fuel spray nozzles in the combustion chambers. The high-pressure fuel cock is the control normally used for starting or stopping the fuel supply to the engine. The high-pressure fuel supply may be mechanically controlled by a lever on the flight deck, or it can be electrically controlled by an actuator, which is also controlled by a switch on the flight deck. When the engine is shut down, any fuel remaining in the fuel manifold would tend to boil as a result of residual engine heat. Solid deposits resulting from the boiling will clog the fuel lines into the system, which would be detrimental to the operation of the engine. The dual inlet line fuel spray nozzle system can utilize a pressurizing and dump valve to prevent this happening. When the engine is shut down, fuel pressure generated by the opening of the high-pressure fuel cock, which was holding the dump valve closed, is lost. The spring inside the dump valve will now be able to open the valve and allow the contents of the fuel manifold to pass back to the supply line. At the same time, the inlet check valve will close, maintaining fuel inside the unit ready for the next start. When the high-pressure fuel cock is opened, a signal of fuel pressure is sent to the dump valve, which moves over and shuts off the fuel flow back to the supply line. In moving over, the valve also opens the passageway to the primary manifold. Fuel pressure from the fuel control unit will open the inlet check valve and pass through the filter to the primary fuel manifold. At a predetermined engine speed, the fuel pressure from the fuel control unit will build sufficiently to open the pressurizing valve, and fuel will also begin to flow into the main manifold, expanding the fuel spray pattern and assisting in better atomization. Many modern gas turbine engine installations utilize electronic engine control to enable better fuel economy, better reliability, and prolonged engine life. Two types of electronic engine control are currently in use: the supervisory engine control system, the full authority digital engine control system. The supervisory engine control system uses a computer which receives inputs of various engine operating parameters and controls a standard hydromechanical fuel control unit. The fuel control unit responds to the electronic engine control commands and performs the functions necessary for engine operation and protection. The computer will monitor EPA, throttle lever angle, Mach number, engine intake pressure, and temperature, and will maintain a constant thrust regardless of changes in air pressure, temperature, or flight environment. Any fault with the electronic engine control will cause the system to revert to manual control. The Full Authority Digital Engine Control System, commonly called by its initial letters FADEC, receives all the necessary data for engine operation and takes over virtually all of the steady-state and transient control functions, which includes compressor airflow control. The hydromechanical fuel control unit is now redundant, except for the throttle valve and fuel shutoff cock, which reduces the mechanical complexity of the engine fuel system. The FADEC system will monitor all of the normal engine parameters and prevent limitations being exceeded while controlling the engine through all modes of operation, for example starting, idle, acceleration and deceleration, takeoff, climb and cruise. In other words, it controls the engine in response to the throttle lever position or the flight management computer thrust demand. The digital computer which is required to run the system has to be considered an essential component of the engine, just as essential as the compressor or the turbine. This is because a complete failure of the FADEC system would cause the complete loss of the engine thrust. To minimize the chances of a single failure causing the loss of an engine, the FADEC system incorporates two separate identical digital channels. Each channel is able to provide information to enable all engine functions. The FADEC system can be powered from the aircraft electrical system, but in most modern aircraft the system is driven by a separate generator fitted to the accessory gearbox of the related engine. This concludes the lesson on engine fuel systems. The adoption of the gas turbine engine as the power unit of choice for military and subsequently civil aircraft became more and more the norm after the end of World War II. During World War II, the war effort required every drop of gasoline, and partly because it was thought that gas turbine engines were relatively insensitive to the properties of the fuel they used, but mainly because it was more available than gasoline, kerosene was chosen to power them. After the war, the United States Air Force started using a fuel in gas turbine engines which spanned the gasoline and kerosene boiling ranges. This fuel was called a wide-cut fuel, a name which stemmed from the position in the catalyzing process from where the fuel could be taken. It was assumed that during wartime conditions, wide-cut fuel would be available in greater volume than either gasoline or kerosene alone. However, when it's compared to a kerosene-type fuel, the higher volatility of the wide-cut fuel gives it some operational disadvantages. At high altitudes, wide-cut fuel evaporates much more quickly. There is a greater risk of fire and explosion when wide-cut fuel is being handled on the ground. A crash of an aircraft fueled with the wide-cut fuel is less survivable than if the aircraft had been fueled with a kerosene-type fuel. Because of these disadvantages, the United States Air Force commenced changing from the use of wide-cut or JP4 fuel back to kerosene-type or JP8 fuels in the 1970s. JP stands for jet propulsion. As far as the commercial jet aircraft industry was concerned, kerosene-type fuel was chosen because it appeared to have the best combination of properties. Having said that, Jet B, which is a wide-cut fuel, is still available in some parts of Alaska and Canada because it's suited to cold climates. In the remainder of North America, Jet A, which is a kerosene-type fuel, is used because of its lower cost and better availability. With the exception of the Commonwealth of Independent States, the rest of the world uses predominantly Jet A1, which is also a kerosene-type fuel. Jet A1 has a higher freezing point than Jet A, which makes it more suitable for use on long international flights. The Commonwealth of Independent States and parts of Eastern Europe use a Russian fuel, TS1, which is a light kerosene-type fuel. Jet fuel is produced in a petroleum refinery by processes that can be divided into three basic categories. They are separation processes, upgrading processes, and conversion processes. In a petroleum refinery, the most widely used separation process is that of distillation. Petroleum products can be defined by their boiling range, and distillation is the process used to separate a mixture with a wide boiling range into products with narrower boiling ranges. The separation is achieved by heating the crude oil in a distillation column until the lightest components are vaporized. The vapors are then collected in a condenser where they turn back into a liquid, which is then collected. The lightest hydrocarbons, propane and butane, rise to the top of the column and are removed first. Gasoline, which is heavier, doesn't rise so high in the column and is drawn off from the side of the column. Kerosene and diesel, which are the next heavier fuels, are drawn off at successively lower points on the column. Finally, the residual, which can be further refined by a catalytic cracking process into lubricating oil, paraffin wax and asphalt, is drawn off at the bottom of the column. The quality of the light products generated by distillation alone is often poor, so the refinery must use conversion processes, like the catalytic cracking just mentioned, and upgrading to bring the fuel to a standard which is suitable for its task. Upgrading processes are used to improve the standard of the fuel by using chemical reactions to remove any compounds which may give it undesirable qualities. One such upgrading process is called sweetening. Sweetening converts sulfur mercaptans in the fuel into disulfides. While sulfur mercaptans are corrosive and have a strong offensive odour, the disulfides are not corrosive, and their smell is less strong. The two leading organisations which set and maintain specifications for civil aviation turbine fuels are, in the United Kingdom, the Ministry of Defence, or the MOD, and in the United States, the American Society for Testing and Materials, ASTM. In the Commonwealth of Independent States and parts of Eastern Europe, gas turbine engine fuels are covered by GOST specification. The specification of an ideal fuel for a gas turbine engine would include the following requirements. The fuel must be able to flow freely from the aircraft's fuel tanks to the engines. Fluidity is a general term that deals with the ability of a substance to flow, but it is not a defined physical property. However, viscosity and freezing points are physical properties, and they can be used to characterize the fluidity of gas turbine fuels. Viscosity is a measure of a liquid's resistance to flow. A thin liquid, like gasoline, has a low viscosity, and a thick liquid, like treacle, has a high viscosity. The viscosity of a liquid increases as its temperature falls. Gas turbine fuel is composed of more than 1,000 individual hydrocarbons, each with its own freezing point, so it does not become a solid at one temperature in the same way that water does. As the temperature of the fuel becomes lower, the hydrocarbons with the highest freezing point freeze first, and form wax crystals. As the temperature drops further, the hydrocarbons with slightly lower freezing points start to solidify, and so on as the temperature falls even lower. Thus the fuel changes gradually from a homogeneous liquid into a liquid which contains a few wax crystals, then to a slushy liquid composed of fuel and wax crystals, and finally to an almost solid block of wax crystals. Small carbonaceous particles are formed early in the combustion process within a gas turbine engine. In ideal conditions within the engine, the particles would be completely consumed, but conditions seldom remain ideal, and if they impinge upon the nozzle guide vanes and rotor blades of the turbine, the particles will erode them. Fuels differ in density and therefore in energy content per unit weight or unit volume. Less dense fuels have a higher energy content per unit weight, as for instance aviation gasoline, which has 18,800 British thermal units per pound. But they have a lower energy content per unit volume. In this case, 112,500 British thermal units per gallon. The relationships are reversed for denser fuels like kerosene, which has only 18,610 British thermal units per pound, but 125,800 British thermal units per gallon. Corrosive compounds are inevitably present in the fuel used to drive gas turbine engines. The corrosive agents include organic acids and sulfur mercaptans, which are potentially very damaging to aircraft fuel systems. Additionally, the fuel becomes contaminated by trace amounts of sodium and potassium, which can corrode the turbine. Ideally, all these should be eliminated from the fuel. The flash point of a liquid is the lowest temperature at which the vapours above a liquid will ignite when they are exposed to an ignition source. The higher the flash point of a fuel, the lower the fire hazard it presents. We have just seen that to burn, the fuel must turn from a liquid state into a vapour. Volatility is a fuel's ability to vaporize, so it's important that the fuel is reasonably volatile. However, if the fuel is too volatile, it will evaporate quickly when the aircraft is at altitude, and it could cause vapour locks to occur at the inlet to the fuel pumps. Lubricity is the ability to reduce friction between solid surfaces which are in relative motion. Gas turbine engine fuels must have a degree of lubricity, because the fuel is used as a lubricant in the pumps. These requirements can be met, and the various methods used to achieve them are discussed later. However, in practice, the cost of satisfying all of them is prohibitive, and therefore compromises have to be made. We've already stated that the gas turbine engines of commercial aircraft would normally use kerosene fuels. The types of fuel which can be used in gas turbine engines are listed here, together with some of their characteristic properties. Jet A1, or AVTUR, which is short for aviation turbine fuel, is a kerosene-type fuel with a nominal specific gravity of 0.8 at 15 degrees Celsius. It has a medium flash point of 38.7 degrees Celsius and a waxing point of minus 50 degrees Celsius. Jet A is also a kerosene-type fuel with a medium flash point, but it has a waxing point of minus 40 degrees Celsius. This fuel is normally only available in the United States. Jet B, or AVTAG, which is short for aviation turbine gasoline, is a wide-cut gasoline kerosene mix-type fuel with a nominal specific gravity of 0.77 at 15 degrees Celsius. It has a low flash point of minus 20 degrees Celsius, a wider boiling range than Jet A1, and a waxing point of minus 60 degrees Celsius. This fuel can be used as an alternative to Jet A1, but, as we stated earlier, with its low flash point, it's a very flammable fuel, and for reasons of safety is not generally used in commercial aircraft. Turbine fuels are not dyed. They retain their natural colour, which can range between what is referred to as water clear to a straw yellow. If a fuel sample is placed in a clean, transparent, dry glass container and swirled vigorously to generate a vortex in the sample, and the sample appears cloudy or hazy, this could be caused by a number of factors. If the cloudiness appears to rise quite rapidly towards the top of the sample, then air is present. If the cloud falls quite slowly towards the bottom of the sample, then water is present in the fuel. Having said that, a cloudy appearance usually indicates the presence of water. A certain amount of water is present in all fuel. The water, which is normally dissolved within the fuel, gives rise to the following fuel system problems. As an aircraft climbs to altitude, the fuel is cooled, and the amount of dissolved water that it can hold is reduced. Water droplets form, and as the temperature is further reduced, the droplets turn to ice crystals, which can block fuel system components. Microbiological fungi called Cladosporium resinae and Pseudomonas aeruginosa are present in all turbine fuels. These fungi grow rapidly in the presence of water to form long green filaments, which join together to form dark, gel-like mats. The filaments and mats can block fuel system components. The waste products of the fungus are corrosive, especially to fuel tank sealing substances. The inclusion of a fuel system icing inhibitor, or FSII, in the fuel will help to overcome these problems. The inhibitor presently in use in all countries except Russia is diethylene glycol monomethyl ether. Not only does it inhibit the ability of the water in the fuel to freeze, it also acts as a pesticide, which retards the growth of the microorganisms in the fuel. Lubricity agents are added to the fuel to compensate for the poor lubricity of some gas turbine fuels to reduce wear in the fuel system components. Gas turbine fuel in its untreated state is a poor conductor of electricity. Static dissipator additives partially eliminate the hazards of static electricity generated by the movement of fuel through modern high-flow rate fuel transfer systems. Corrosion inhibitors protect ferrous metals in fuel handling systems, such as pipelines and storage tanks, from corrosion. Certain of these corrosion inhibitors appear to improve the lubricating qualities, the lubricity, of some gas turbine fuels. Metal deactivators suppress the catalytic effect which some metals, particularly copper and zinc, have on fuel oxidation. Copper and zinc are not used in most jet fuel distribution systems or gas turbine engine fuel systems, but if the fuel does become contaminated with either of these metals, metal deactivators inhibit their catalytic activity. We've already stated that water is always present in fuel. The amount will vary according to the efficiency of the manufacturer's quality control and the preventative measures taken during storage and transfer. Further measures can be taken to minimize water accretion once the fuel has been transferred to the aircraft tanks. If the fuel can be allowed to settle after replenishment, then the water droplets, being heavier than the fuel, will fall to the bottom of the tank and can then be drained off through the water drain valve, which is situated in the lowest part of the fuel tank. Heating the fuel before it's passed into the more sensitive components of the system will assist in preventing ice formation. In gas turbine engine fuel systems, the fuel is passed through a heat exchanger which is powered by compressor delivery air to melt any ice crystals which may have formed while the fuel was exposed to the very low temperatures experienced at high altitudes. Some systems also utilize a fuel-cooled oil cooler. This has an added attraction in that we appear, just for once, to get something for nothing. After all, the oil has to be cooled, and the fuel benefits by being warmed, so 2 jobs for the price of 1. Once the fuel is in the aircraft fuel tanks, the main source of water contamination is the atmosphere that remains within the tank. If the tanks are topped up to full, then the atmosphere is excluded, together with the moisture it contains, thus minimizing the likelihood that the fuel will be contaminated. Caution is required here. Filling up the tanks may prove an embarrassment the next day if the ambient temperature rises. The volume of the fuel in the tank will increase, and there is the danger that it may spill out of the vent system. We've already spoken of the process whereby, as the temperature of kerosene becomes lower, the hydrocarbons in the fuel which have the highest freezing point freeze first, and form wax crystals. The wax crystals can clog the fuel filter and interfere with the operation of the fuel control unit. The effects of waxing can be minimized by the refinery keeping the levels of heavy hydrocarbons in the fuel to a low level, and the inclusion of a fuel heater in the engine fuel system. The specific gravity of a liquid varies inversely with its temperature. The heat release from the fuel is directly related to its specific gravity, and so changes in fuel density can change the power output of an engine. On modern aircraft this usually makes little difference, as modern fuel control units will automatically compensate for the change in density of the fuel. Remember, though, that a change in specific gravity will also change the weight of the aircraft. Specific gravity is also known as relative density. This concludes the lesson on gas turbine engine fuels. Besides the primary reason of reducing friction, there are secondary reasons for having a lubricant within the engine. Even if the engine was kept scrupulously clean, there will always be small amounts of dirt or impurities that find their way inside it. That dirt must be removed from the oil before it can cause damage to bearings or block small oil passageways within the engine. The oil keeps the interior of the engine clean by carrying any contaminants in suspension in the lubricant to the oil filter, where they're removed. The majority of the bearings within the engine are manufactured from steel, a metal which would soon oxidize itself if it were not prevented from doing so by a liberal coating of oil. Thus the lubricant also minimizes corrosion inside the engine. The bearing surfaces in the engine, particularly those towards the turbines, must be cooled if they are to be able to withstand the constant heat stresses imposed upon them. The lubricant is used to take the heat away from the bearing surfaces and transfer it to the oil cooler, where it's dissipated into the atmosphere. A further task of the lubricating oil is that of being a hydraulic fluid. For instance, in some turboprop engines, the control of the pitch of the propeller blades is achieved by using the engine lubricating oil to operate the pitch change mechanism. Most gas turbine engines use a self-contained recirculatory lubrication system in which the oil is distributed around the engine and returned to the oil tank by pumps. There are two basic recirculatory systems which we'll investigate here. They are the pressure relief valve system and the full flow system. The pressure relief valve, which gives its name to this type of lubricating system, is situated in parallel with the oil pressure pump. It limits the pump outlet pressure by diverting any excess volume back to the inlet of the pump, thus controlling the flow of oil to the bearing chambers. The engine oil pressure is restricted to a value which the engine designer considers correct for all conditions that the engine might encounter. The pressure relief valve will begin to relieve pressure at the value which is generated by the oil pressure pump at engine idling speed. As a consequence, the pressure relief valve theoretically maintains a constant pressure over the whole of the engine's speed and oil temperature ranges. This diagram shows the basic components required in the pressure relief valve lubrication system of a turboprop engine. The oil is drawn to the pressure pump through a suction filter. The suction filter protects the pressure pump from damage should any debris enter the tank. The oil pressure pump is contained within an oil pump pack. The oil pump pack contains one pressure pump and several scavenge pumps. Having several scavenge pumps ensures that the lubrication system remains a dry sump system. From the pressure pump, the oil is passed through the pressure filter, which removes any small particles which may block the feed jets. The oil then flows to the pressure relief valve, which maintains the oil pressure to the feed jets in the bearing chambers constant. The oil is passed to the feed jets through internal drillings and external oil pipes. In this particular engine, the hollow interior of the compressor turbine shaft is used to transfer oil from the front of the engine, where it's used in the pitch control mechanism, all the way through to the rear of the engine, where it's used to lubricate and cool the turbine bearings. The torque meter pump shown in this diagram is used to boost engine oil pressure to a figure which is considerably higher than normal system pressure. In some turboprop engines, the torque meter pump output can be as high as 600 pounds per square inch. Torque meter pressure is utilized to balance the axial thrust of the helically cut gears within the propeller reduction gear. The axial thrust is proportional to engine power output. When the oil has completed its task of lubricating, cooling, cleaning and acting as a hydraulic medium, it falls into collecting trays or compartments from where it makes its way to the scavenge pumps. The scavenge pumps push the oil through an air-cooled oil cooler, where the heat is dissipated into the atmosphere. From the oil cooler, the oil travels to the de-aerator tray, where any air bubbles, which will have been formed in the oil, escape, and the oil falls to the oil tank, which in this case is contained around the engine intake. Any air pressure which has been built up within the engine lubrication system, through leakage from seals or from the de-aerator tray, must be allowed to escape. If the air pressure was just vented to atmosphere, then any oil mist contained within it will pass to atmosphere also. Thus the oil contents would quickly diminish. To prevent any loss of oil occurring in this manner, the oil mist is vented via a centrifugal breather, which is fitted to and driven by the accessory gearbox. The full-flow lubrication system achieves the required oil flow to the engine throughout its entire speed range by allowing the oil pressure pump to supply the oil feed jets directly, without the use of a pressure relief valve. Using this type of system allows the use of smaller pressure and scavenge pumps, since the volume of oil passed by them is less than that which is passed by the pumps in the pressure relief valve system. This discrepancy in the volume of oil used in each of the two systems exists because of the large amount of oil which is spilled back, either to the oil tank or the inlet of the pressure pump, in the pressure relief valve lubrication system at high engine speed, whereas no excess pressure is generated in the full flow system. The pressure pump picks up oil from the oil tank through a suction filter. The high-pressure oil generated by the high-pressure pump passes through a pressure filter to the distribution galleries. Fitted across the pressure filter is an oil differential pressure switch. The oil differential pressure switch will give a warning of filter blockage. This warning is usually indicated at the ground crew servicing panel, and is sometimes duplicated by a warning light on the flight deck. The upper portion of the oil gallery transfers the oil to an oil pressure transmitter and low oil pressure warning switch. These items are used primarily to give warning in the cockpit of malfunctions in the oil system. Other parameters indicated in the cockpit are those of oil quantity and oil temperature, the latter being measured as the oil leaves the oil cooler. A tapping from the upper portion of the gallery transfers oil to lubricate all of the bearings in the accessory drive gearbox. The lower portion of the gallery is used to transfer oil to the bearings which support all of the compressor spools. The bearings are lubricated by oil jets, which are positioned very close to the bearings. This minimizes the possibility of the oil being deflected from its target by local turbulence. Thread-type filters are fitted in the oil supply line just before the oil jets. Thread-type filters perform the function of a last-chance filter, removing any debris which may have managed to pass through the main pressure filter. In a similar manner to the pressure relief valve system, when the oil has completed its tasks, it's collected by scavenge pumps. Prior to the oil reaching the scavenge pump, it passes over a chip detector and through a suction filter. The scavenge pumps pass the oil to the oil cooling system. This engine utilizes two types of oil cooler, a fuel-cooled oil cooler and an air-cooled oil cooler. Normally the fuel-cooled oil cooler is sufficient to cool the oil on its own, but in the event that it proves inadequate, a valve opens automatically and brings the air-cooled oil cooler into operation as well. We mentioned earlier that air pressure escaping from seals cannot be allowed to build up within the engine. In this engine, air pressure within the engine is vented through the hollow shaft of the drive between the intermediate gearbox and the external gearbox, leaving the external gearbox via the centrifugal breather. The oil tank is normally a separate unit mounted on the side of the engine, although it can be part of the engine intake, or even an integral part of the accessory drive unit. Whatever form the oil tank takes, it must incorporate provision for filling, either by gravity and or more normally from a pressure source. There must also be some method of determining the contents of the tank, either by a sight glass or by a dipstick. Sometimes both methods are used. A de-aerator tray removes air bubbles from the oil as it flows back into the tank. Gear-type pumps, which consist of a pair of intermeshing steel gears located within a close-fitting aluminium housing, are the normal method of delivering and retrieving oil in a recirculatory system. This diagram shows a gear-type oil pump. When the gears are rotated, oil is drawn into the pump, carried round by the teeth, and delivered at the outlet. The oil pumps, both pressure and scavenge, are fitted on the accessory housing. The oil pumps are fitted within an oil pump pack, which consists normally of one pressure pump and perhaps as many as 7 scavenge pumps. Having several scavenge pumps ensures that the lubrication system remains a dry sump system. Oil coolers can be either air-cooled or fuel-cooled. We've seen that some engines use both systems. If an engine does use both air and fuel to cool the oil temperature can be monitored electronically, and the air cooler switched in only when it's deemed necessary. The oil temperature is maintained at a value which helps to improve the thermal efficiency of the engine. Whether it is fuel-cooled or air-cooled, the oil cooler is basically a radiator, which exchanges heat from one medium to another. The oil cooler consists of a matrix assembly, which is partitioned by baffle plates. The baffle plates ensure that the oil takes the longest path through the matrix, and it thus gains maximum benefit from the cooling effect of the fuel flowing through the tubes within the matrix. The fuel-cooled oil cooler has a double benefit. The fuel in the aircraft wing tanks is invariably very cold, and requires warming up before it gets to the fuel filter. The oil is hot and requires cooling. This device allows both requirements to be carried out within it, a rare chance of achieving 2 for the price of 1. Incorporated in the fuel-cooled oil cooler is an oil bypass valve, which is fitted across the oil inlet and outlet. If the oil cooler becomes blocked, when the oil pressure in the cooler inlet zone reaches a predetermined value, the oil bypass valve communicates directly between the oil inlet and the oil outlet. This will prevent oil starvation in the engine, and will also preclude the chance of excess oil pressure damaging the relatively fragile matrix assembly. In the event that damage to the oil cooler matrix does occur, fuel is prevented from entering the oil system by the oil pressure being kept at a value higher than the fuel pressure. This is done by a pressure-maintaining valve located in the oil feed line to the cooler. Thus the oil will leak into the fuel system rather than the other way round. Chip detectors, which are permanent magnet plugs, are situated in some of the scavenge lines to collect ferrous material from the oil as it returns to the scavenge pumps. The chip detector is retained in the pipeline by a bayonet fitting within a self-sealing housing. The fact that the valve housing is self-sealing means that the detector can be removed without any loss of oil. Contamination of the magnet by iron filings is illustrated here. This type of contamination can be taken as evidence of impending failure in the bearing chamber, which is being monitored by that particular chip detector. We've already stated that to prevent excessive air pressure within the accessory drive unit and the bearing chambers, the interior of the engine must be vented to atmosphere. Airborne oil droplets in the air within the engine form an oil mist which, if it was allowed to escape unhindered, would rapidly deplete the engine oil contents. The oil mist is vented to the accessory drive unit, where it must pass through the centrifugal breather before reaching the atmosphere. The centrifugal breather is rotated at high speed, and as the oil mist enters, it's thrown outwards by centrifugal force. Around the inside periphery are de-aerator segments. The oil is separated from the air and is eventually flung back into the accessory drive unit to be picked up by a scavenge pump. The air, having less inertia, makes its way out of the centre of the rotating portion of the breather to atmosphere, having had all of the oil removed from it. Thus, the centrifugal breather minimises oil loss in the gas turbine engine. To facilitate the oil's task of cleaning, a number of filters and strainers are positioned within the lubrication system. The filters and strainers prevent debris and foreign matter from being continuously circulated around with the oil. As we described earlier, the oil is drawn from the oil tank through a suction filter before it goes into the pressure pump. The suction filter takes the form of a coarse strainer, which prevents debris being drawn into the pump and damaging it. At the outlet of the pressure pump, a pressure filter is fitted. This is a very fine mesh filter, which will retain any small particles which might block the oil feed jets. Thread-type filters perform the function of a last chance filter immediately prior to the oil jets. Each return oil line contains a scavenge filter just downstream of the magnetic chip detector. These scavenge filters will collect any debris returning from the bearing chambers. Both pressure and scavenge filters are constructed in a tubular form from either a very finely woven wire cloth or resin impregnated with fibres. Some filters may have a differential pressure switch fitted across them, or alternatively they may be fitted with a pop-up indicator, a small button which can be seen protruding from the filter casing to give a visual warning of a partially blocked filter. Gas turbine engine oils must have a high enough viscosity for good load carrying capacity, but they must also have a sufficiently low viscosity to ensure a good flow of oil at low temperatures, as would be the case, for instance, when starting after a prolonged cold soak. Early gas turbine engines used the same oils as had been used in petrol engines for years. These oils were mineral-based. It was found that under the higher temperatures and speeds at which gas turbine engines operated, mineral oils burnt, scummed, and oxidized. To attain the properties mentioned at the beginning of this lesson, synthetic oils were developed. Synthetic oils have the following qualities: low volatility to prevent evaporation at high altitudes, a high flash point which will prevent the lubricant igniting at high temperature points within the engine, such as at the turbine bearings, a high film strength which gives the oil molecules the ability to stick together under compression loads and adhere to surfaces under centrifugal loads, a wide temperature range. Most gas turbine lubricating oils have a temperature range of minus 45 degrees Celsius to plus 115 degrees Celsius. A low viscosity, which increases the ability of the oil to flow under low temperature conditions. A high viscosity index, which is an indication of how well the oil retains its viscosity when heated to its operating temperature. Low viscosity oils can be used in gas turbine engines because of the absence of reciprocating parts and heavy-duty gearing. However, turboprop engines, which have reduction gears and propeller pitch change mechanisms, require a slightly higher viscosity oil. Gas turbine engines are invariably dry sump engines. The oil level of a dry sump engine should be checked immediately after engine shutdown, or at least within a specified time after engine shutdown. This concludes the lesson on lubrication. The first recorded use of an auxiliary power unit was on a four-winged interceptor aircraft in the Great War in 1916. The aircraft, called the Nighthawk, was designed and built by the owner of the firm that would eventually become Supermarine, the builders of the Spitfire. A gasoline-fueled piston engine was used in this particular instance. However, because aircraft in general, and commercial aircraft in particular, began to need more powerful electrical and hydraulic supplies and air conditioning facilities to service them while they were on the ground with their engines shut down, the auxiliary power unit, which was to satisfy these requirements, became more sophisticated. Aircraft manufacturers and operators also recognized the fact that because it had an auxiliary power unit, it also meant that the aircraft was no longer dependent on expensive ground support equipment. The auxiliary power unit can provide the necessary power for operation of an aircraft's electrical, hydraulic, and pneumatic systems. While earlier aircraft used the piston engine to drive their auxiliary power units, it soon became obvious that the gas turbine engine was safer, lighter, quieter, and more reliable. The gas turbine engine auxiliary power unit uses AVTUR, which is the same fuel as the main engines use, so the problem of fuel storage and fuel management systems is minimized. The type of gas turbine engine normally used to drive auxiliary power units is a turboshaft engine with a free turbine. The free turbine, which is designed to run at a constant speed, drives the accessories via a gearbox. The fact that the free turbine runs at a constant speed ensures that the auxiliary power unit's generator maintains a constant frequency without the need for an additional constant speed drive unit. Some aircraft use air bled from the auxiliary power unit's compressor to power the aircraft's pneumatic system, but it's also common for the free turbine to drive a separate load compressor to supply bleed air. The auxiliary power unit is normally positioned in the tail of the aircraft, where its operation will not harm personnel working in proximity to the aircraft. The auxiliary power unit of modern aircraft can be operated in the air, thus providing a backup source of power to the aircraft systems in the event of an engine failure. This ability to operate while airborne has become more important with the introduction of twin-engine aircraft, which are now flying long-haul routes under extended twin operations (ETOPS) regulations. Auxiliary power units fitted to ETOPS aircraft must be extremely reliable, as they are used in place of the failed engine to supply backup electrical and pneumatic power during single-engine operations. While other auxiliary power units may or may not have the ability to be started while the aircraft is in flight, ETOPS-compliant auxiliary power units must be capable of being started at all altitudes. If such auxiliary power units malfunction, the aircraft cannot be released for ETOPS flight and must fly a longer route. While, for example, the L-1011 TriStar can start its auxiliary power unit up to 25,000 feet and has the capability of delivering power up to 31,000 feet, the Allied Signal auxiliary power unit, which is fitted in some Boeing 737 aircraft, has a 41,000-foot start capability and can deliver 66 kVA at this altitude. If the aircraft descends to 31,000 feet, that same auxiliary power unit can deliver 90 kVA. Other 737 aircraft may have Garrett or Sunstrand auxiliary power units fitted. These units have a maximum recommended start altitude of 25,000 feet and are only rated at 55 kVA. These two auxiliary power unit control panels from the Boeing 767 and the Airbus A320 aircraft illustrate that the pilot has very little control or indication of what's happening on the auxiliary power units fitted to modern aircraft. On older aircraft, such as the earlier Boeing 737 series, the auxiliary power unit panels incorporate load meters and EGT gauges, as well as indicator lights which warn of low oil quantity, low oil pressure, high oil temperature, and overspeed. The auxiliary power unit's turboshaft engine is started by an electric starter motor powered from the aircraft battery, although some later model aircraft have a dedicated auxiliary power unit battery to preserve the aircraft batteries. When the auxiliary power unit is started, the RPM and EGT must be allowed to stabilize before it's used to power the aircraft systems. It is possible on older aircraft to see the RPM and EGT gauges. On more modern aircraft where gauges are not available, it may be possible to hear the APU RPM stabilize. The stabilization of the EGT should follow that very closely. The auxiliary power unit may not be able to completely power all of the aircraft systems. For instance, on some aircraft, the galley power will be load shed automatically if the auxiliary power unit load reaches a maximum value. Additionally, if the auxiliary power unit EGT reaches a predetermined figure, then the bleed air valve will begin to close, reducing the ability of the auxiliary power unit to supply the pneumatic system. It's usual for the auxiliary power unit to be operated for a cooling period of at least 1 minute with no pneumatic load prior to shutdown. The auxiliary power unit will automatically shut down for the following reasons: fire, low oil pressure, high oil temperature, overspeed. The auxiliary power unit has only one fire bottle, which uses Freon, stored at a pressure of approximately 800 psi as the extinguishant. Operation of the auxiliary power unit fire handle passes an electrical supply through a cartridge, which ruptures a diaphragm in the outlet of the bottle. When the diaphragm breaks, the internal pressure forces the extinguishant into the auxiliary power unit shroud, where it suffocates the fire. The indication that the cartridge has fired is given by the displacement of a yellow disc, which is positioned on the side of the aircraft, where it can be checked during the walk-round inspection. The red disc alongside the yellow disc will become displaced if the fire bottle has become too hot or its internal pressure has become too high. Just as it would be impossible to fly a large modern aircraft safely without the flight instruments, it would also be impossible to fly it safely without the engine and aircraft systems instruments. The engine instruments are divided basically into two categories that are called either the performance indicators or the engine condition indicators. Performance indicators are thrust indicating instruments, such as the engine pressure ratio (EPA) gauge, or the fan speed (N1) gauge. Engine condition indicators include the exhaust gas temperature (EGT) gauge, compressor speed, oil pressure and oil temperature gauges. We'll be discussing these and others later in the lesson. This diagram shows some of the parameters that we've just mentioned, and the position of the sensors that are required to measure them. There are two types of cockpit display: the analog display, a clockwork cockpit, or the electronic display, a glass cockpit. We'll be showing some of the instruments required in the clockwork cockpit as we go through the lesson. The glass cockpit displays will be described in detail in the latter part of the lesson. In the clockwork cockpit, there is a multitude of gauges displaying information. The glass cockpit is displayed on cathode ray tubes, CRTs, or liquid crystal display panels, LCDs, with light-emitting diodes, LEDs, for digital displays. Alongside the glass cockpit display, a small number of conventional gauges are retained in case of failure of the electronic displays. Both types of display convey essentially the same information to the pilot, but the flexibility of the glass cockpit system means that it's now taking over as the preferred means of showing both flight and engine instrumentation. Thrust measuring instruments are of two basic types. The type that measures the jet pipe pressure, the P7 gauge. The type that measures the ratio of two parameters, the jet pipe pressure and the engine air intake pressure, the EPA gauge. Turbopropeller aircraft measure and indicate engine torque, which is used to give an indication of engine power. Older low-ratio bypass engines, like the Rolls-Royce Conway, use the jet pipe pressure, P7, as an indication of engine power. The P7 system gauge can be marked in inches of mercury, pounds per square inch, or a percentage of the engine's maximum thrust. High-ratio bypass engines use the engine pressure ratio, EPA, as an indication of engine power output. The ratio is that between the exhaust pressure and the engine intake pressure. On some large turbofan engines, the values of the turbine discharge pressure and the fan outlet pressure are integrated. The figure thus obtained is then compared to the compressor inlet pressure to produce what is called integrated EPA. Pitot tubes, suitably positioned, sense the pressures which are required to work the system. The tubes can either be connected directly to the indicator in the cockpit or to a pressure transmitter which is electrically connected to the indicator. Turboprops and turboshaft engines develop their power by producing a preponderance of torque to turn the propeller, rather than pure thrust from their jet efflux. Torque, by definition, is a force applied at a distance to a turning point. The torque meter system measures, and its indicator displays, the power being produced by the engine. There are two main methods employed in measuring the torque of the engine. One uses oil pressure, and the second is an electronic device. The units of measurement vary between systems. The indicator gauges may be calibrated to read pounds per square inch or foot-pounds, Newton meters, brake or shaft horsepower. Engine torque is proportional to the horsepower being produced by the engine, and this is transmitted through the propeller reduction gear. The helical gear torque meter system depends on the axial thrust which is developed when helically cut gears are used to transmit power through the propeller reduction gear. The shafts of the gears rotate within cylinders, and the axial thrust they develop is balanced by oil pressure trapped inside the cylinders. Torque meter oil pressure is transmitted to a gauge in the cockpit. The gauge is calibrated in pounds per square inch. The system oil pressure, which in some systems can have quite a high value, for instance the Proteus engine is capable of developing about 800 pounds of torque, is generated by a torque meter system oil pump. In this system, which is similar to that used on the Rolls-Royce Dart engine, there is an oil pressure bleed hole within each cylinder. When the thrust developed by the helically cut gear is exactly balanced by torque meter oil pressure, the shaft of each helical gear takes up a sensitive position, partially covering the bleed hole. If engine power output increases, the axial thrust being transmitted by each gear increases, which forces its shaft further into its retaining cylinder. Thus the shaft is forced into a new position where it blocks the bleed hole. The torque meter oil pressure, being unable to escape, now builds up to a new, higher value, until it's able to force the gear shaft back into the sensitive position, where once again it's able to balance the axial thrust being developed by the helical gear. If the engine power output decreases, the axial thrust being transmitted by each gear also decreases, which allows its shaft to be displaced slightly out of the retaining cylinder. Thus the shaft is forced into a new position where it uncovers the bleed hole. The torque meter oil pressure now falls to a new lower value, until the lower axial thrust being developed by the engine is able to overcome it and force the gear shaft back into the sensitive position in the cylinder. Once this has happened, axial thrust is again balanced by oil pressure in the cylinder, but now it's balanced by a lower torque meter value. In addition to giving an indication of engine power output, the torque meter system can also be utilized to send signals to the auto feather and the water methanol injection systems. The auto feather system, as its name implies, will automatically feather the propeller of a failed engine. This is particularly important if the failure occurs on takeoff. The electronic system comprises two concentric shafts. The first shaft, which is called the torque shaft, connects the engine to the propeller reduction gearbox. The second shaft, the reference shaft, is connected only to the engine. An exciter wheel is fitted to the forward end of each shaft. The exciter wheels rotate past an electromagnetic pickup and produce an AC voltage. While the engine is stationary, the exciter wheels are aligned, but as power is increased, the torque shaft twists. This changes the phase relationship of the voltages produced. The change in phase relationship, which is used to drive an indicator through an amplifier, is proportional to the change in power. The RPM indicator is called a tachometer, tacho for short. There are three methods of measuring engine rotational speeds: the mechanical magnetic tachometer, the electrical generator system, the tacho generator, the inductive probe system. The measurement of engine speed is of vital importance if accurate control and monitoring of the engine can be achieved. The crankshaft speed of piston engines is measured. The RPM indicator is called a tachometer, a tacho. The usual method of measuring engine rotational speed on piston engines is the mechanical or magnetic tachometer. The mechanical tachometer consists of a flexible drive shaft and the tacho indicator. One end of the flexible drive shaft is connected to the tacho indicator in the cockpit. The other end goes to the accessory drive casing on the engine, where it's driven through gears from the crankshaft. The input drive causes a magnet in the indicator to rotate. The magnet rotates inside a copper or aluminium drag cup. This induces eddy currents in the aluminium drag cup. Eddy currents are caused by the magnetic field of the moving magnet acting on the electrons of any metal in the vicinity of the magnet. The eddy currents themselves generate a magnetic field which interacts with the magnetic field of the magnet. This interaction causes a torque or turning moment, which is established to turn the drag cup in the same direction as the permanent magnet. A shaft extends from the drag cup and is connected to a pointer. The turning motion of the pointer is against the tension of a hairspring, which controls the drag cup position and hence the position of the pointer. The flexible drive is driven at reduced speed, but true speed will be shown on the indicator. The indicator incorporates compensation devices for changes in temperature. The electrical generator system, sometimes called the tacho generator system, is possibly the oldest form of engine speed measurement still in use on large aircraft. It utilizes a small three-phase generator, driven by the appropriate spool shaft. The output of this generator powers an indicator in the cockpit. The indicator is a synchronous squirrel cage motor that turns a drag cup assembly. The drag cup moves a pointer over a scale in a similar manner to that which we've just seen used in the mechanical system. In older aircraft, the indicator showed the actual revolutions per minute of the engine, but it's much more common to have the speed displayed as a percentage of the maximum engine speed. The speed of rotation of each of the spools is displayed. N is the SI symbol for rotational speed. Thus, in a triple spool engine, the speed of the low-pressure compressor, the fan, would be displayed as N1. The intermediate spool speed would be shown as N2, and the high-pressure compressor rotational speed would be N3. It's probable that there would always be provision on the high-pressure compressor spool for driving a tacho generator through the external gearbox, which is driven by the high-pressure compressor shaft. But it may not always be possible to have gearboxes driven by the other compressor shafts. In this case, a speed probe could be used. There are two ways that the speed probe can generate the pulses required to feed the system. The first method uses the fan blades to excite the magnetic field of the sensor head of the speed probe as they pass it. The excitations generate a waveform which has a frequency proportional to the rotational speed of the fan. The second system uses a phonic wheel, which is part of the compressor shaft. The teeth of the phonic wheel pass through the magnetic field of the sensor, and thus generate pulses at a frequency which is proportional to the rotational speed of the shaft. The output of the sensor is amplified before being sent to the gauge. The advantage of the speed probe system is twofold. First, the reduction in the number of moving parts required in the engine, and second, that a number of separate electrical outputs additional to those required for speed indications can be provided, for example, automatic power control and flight data acquisition systems. RPM indicators which receive their speed signals directly from speed sensors or via servo-operated systems are powered from the aircraft supply. In the event of either a power supply failure or a signal failure, the needle of the indicator is returned to an off-scale position, and a power-off flag may be displayed. Clockwork cockpit instruments have displays which show percentage rotational speed, with 100% corresponding to the maximum spool RPM. Two scales are used: a main scale calibrated 0 to 100% in 10% increments, and a second pointer displays rotational speed in 1% increments. In line with other instruments, coloured arcs or indicator lines are used to show ranges and limits of engine speed. A green arc will represent the normal operating range, and an amber arc will denote a caution range. Red arcs show either the maximum speed of the engine or RPM ranges which are restricted, perhaps because vibration may be encountered within them. The glass cockpit uses a mixture of analog and digital displays on the same dial. This type of analog display is very useful in two ways. Firstly, for instantaneous comparison of multi-engine states, and secondly, the digital readout is a very accurate indication of individual engine states when they're required. If a parameter limitation is exceeded in the glass cockpit type of display, the whole of the dial displaying that particular parameter will change to either amber or red, depending on how far the limitation has been exceeded. On some older glass cockpit instrumentation, vertical ribbon displays are used. Many multi-engine aircraft are provided with a visual indicator, which is called a synchroscope, which indicates the RPM difference between the slave engines and the master. As you can see from this picture, the presentation consists of miniature propellers which rotate to show when an RPM difference exists, and whether the slave is faster or slower than the master. Gas turbine engines are heat engines. The power gas turbine engines produce is directly proportional to the heat released during the combustion of the fuel. Engine components and systems are designed to withstand certain temperatures. If their temperature limits are exceeded, they will fail. To allow safe operation, the engine temperatures must be monitored. The following temperatures are monitored on gas turbine engines: engine air inlet temperature, exhaust gas temperature, engine oil temperature, and internal air systems temperature. The temperatures monitored may range from minus 56 degrees Celsius to plus 1200 degrees Celsius. Different sensors are used depending on the temperature range to be monitored. There are 4 major types of temperature measuring device. They are the expansion type, which relies on the principle that most solids, liquids, and gases expand and contract with temperature changes. Two examples of the expansion type of device are the mercury thermometer and the bimetallic strip. The vapor pressure type of device uses the principle that liquids, when subjected to a rise in temperature, change their state from liquid to vapor. By measuring the pressure of the vapor, an indication of temperature can be gained. A change in the temperature of some electrical conductors, for instance platinum, will cause a change in the electrical resistance of that conductor. Measuring the change in the resistance of this conductor will indicate its temperature. This type of sensor is called the resistance type or the temperature bulb. In 1822, Thomas Seebeck accidentally discovered that heating the junction of two dissimilar metals will produce an electrical potential that is a function of temperature. If the junction is contained within a closed loop, the value of the potential will be dependent on the difference in the temperature between the junction where the heat is applied, the hot junction, and the other end of the loop, the cold junction. Examples of the use of thermocouples include the measurement of cylinder head temperature and turbine gas temperature. A radiation pyrometer is a device which can convert radiated energy into electrical energy. It consists of a photovoltaic cell and a lens which focuses the radiated energy onto the cell. The pyrometer is positioned so that the lens can be focused directly onto the heat source, in this case the turbine blades. The photovoltaic cell converts the radiated energy emitted by the blades into electrical energy, which is passed through an amplifier to an instrument calibrated in degrees Celsius. The temperature of the gas passing through the turbine of a gas turbine engine is the most critical parameter of those displayed on the engine instruments. Operation of the engine beyond the limits of turbine temperature, even for only a moment, is liable to cause excessive turbine blade creep, which will be catastrophic if the rotating blades touch the casing of the engine. The gas temperature must be monitored closely, and automatic temperature limiting equipment is fitted to most gas turbine engines operating today. To enable this monitoring to be achieved, temperature probes are inserted in the gas stream. Temperature probes are formed from the junction of two dissimilar metals, which, as we've just seen, generate a potential when the junction is heated. The potential is proportional to the temperature applied to the junction. This diagram shows how the terminals for the connections to the probes, which are the hot junctions, are connected, and also how the gas flows over them. The output from the probes is sent to the cockpit engine instrument, which is the cold junction. Here the potential is displayed on a very sensitive millivoltmeter calibrated to show the engine gas temperature. A single probe would not supply enough information to accurately tell the pilot what was going on in the whole of the turbine. It could only inform him about a small part of the turbine that it was monitoring. Additionally, a failure of that single probe would rob the pilot of his knowledge of the most important of the engine parameters. To gain complete awareness of the temperature situation, it's necessary to place a number of probes around the periphery of the turbine or the exhaust system. The probes are connected electrically in parallel. Their output is thus the average of all of the probes. Connecting the probes in parallel has the added advantage that if one probe is damaged, their electrical output, and therefore the temperature reading on the gauge, is virtually unaffected. The position of the probes in the engine depends upon two things: the anticipated maximum temperature of the gas and the ability of the probe material to withstand that temperature. The industry standard for the material used at the junction in the temperature probes in gas turbine engines is chromel, nickel-chromium, and alumel, nickel-aluminium. These two materials may not have the highest millivoltage output of the materials available, but their ability to withstand very high temperatures coupled with a reasonable volts per degree ratio, makes them ideal for the job. The system does not require a power supply for the gauges to work. However, if the potential generated by the probes is to be used to supply a temperature limiting system, the output will need to be amplified. The power required for amplification will be supplied by the aircraft's electrical system. If it's required that the probe supply both a temperature limiting system, otherwise known as a top temperature control, and a temperature indicating system, they will contain two separate junctions, one to feed the temperature limiting system and one to feed the indicator. On the type of engine where the temperature of the gas within the turbine is too high for the metal of the probes to stand it, the probes may be positioned after the turbine and the gauge calibrated to read exhaust gas temperature, or EGT. On other engines, it may be found convenient to combine the temperature probes with the pitot probes, which measure exhaust gas pressure, P7. In this case, the gauges will read jet pipe temperature, or JPT. Obviously, it would be ideal if the temperature could be sampled either before the turbine, when it would be called either turbine inlet temperature, or TIT, or turbine entry temperature, TET. Alternatively, the gas temperature could be sampled inside the turbine, when it would be called turbine gas temperature, or TGT. In every case, the position of the probes is dependent upon their ability to withstand the temperatures they encounter. Actual blade temperature can be measured by the radiation method, with the use of an optical pyrometer. Air temperature is one of the basic parameters used to establish data vital to the performance monitoring of aircraft engines, for example, thrust settings, fuel-air ratio settings, etc. The ideal temperature to suit these requirements is that sensed under static conditions at various flight levels. This temperature is called variously the outside air temperature or static air temperature, SAT. Unfortunately, this measurement can be affected by the adiabatic compression that occurs with increase of aircraft speed. Below 0.2 Mach, the temperature of the air sampled is very close to SAT. But at higher Mach numbers, an increase in skin friction will raise the air temperature. This increase in air temperature is commonly referred to as ram rise, and the temperature that's indicated is called ram air temperature, RAT, which is the static air temperature plus the increase caused by the ram rise. The ram rise can be computed by air data computers to correct the indicators to SAT, or alternatively calculated mathematically for each type of aircraft as a function of Mach number, and tables or graphs can be included in their flight manuals. For use in the instruments of aircraft which fly at high Mach numbers, total air temperature, TAT, is measured. The air is brought to rest, or nearly so, without the addition or removal of heat. Total air temperature equals static air temperature plus ram air temperature plus friction rise. Temperature indicators use coloured arcs to show their operating range. Green for normal, amber for caution, and red upper or lower limits. Pressure is defined as force per unit area. Pressure is normally indicated either as pounds per square inch or inches of mercury. When we're discussing pressure measurement, we must use the following terms: absolute pressure and gauge pressure. Absolute pressure is measured relative to absolute zero pressure, the pressure that would occur at absolute vacuum. Thus, the absolute pressure on the Earth's surface at sea level is the atmospheric pressure, which is 14.7 pounds per square inch. The more usual pressure measured by most gauges is called gauge pressure. Gauge pressure reflects an adjusted pressure that reads zero at the Earth's surface. Elastic pressure sensing elements are used to measure pressure. Forces are produced within the elements by applied pressures, and these forces are converted to mechanical movement. The mechanical movement is then used to operate either a direct reading gauge or an electrical transmitter. The sensing elements commonly used are diaphragms, capsules, bellows, and Bourdon tubes. A diaphragm is a sheet of a semi-flexible material, anchored at its periphery, and most often round in shape. It usually serves as a barrier between two chambers, moving slightly into one chamber or the other, depending on differences in pressure. Diaphragms are used to measure low pressures. Capsules are made up of two diaphragms placed together and joined at their edges to form a chamber. The chamber may be sealed, in which case the device is called an aneroid capsule, or it may be joined to a pressure source, in which case it's called a pressure capsule. Like diaphragms, capsules are also used to measure low pressure, but capsules are more sensitive to small pressure changes. The bellows element can be considered as an extension of the corrugated diaphragm principle. It may be used for high, low, or differential pressure measurement. Typically, the bellows element is used to measure pressures like the output of an aircraft low-pressure fuel booster pump. The Bourdon tube is the oldest of the devices used for sensing pressure. The element is essentially a length of metal tube with an elliptical cross-section and shaped into a letter C. One end of the tube is sealed and called the free end. The other end is connected to the pressure source and fixed. When pressure is applied, the tube tries to straighten. This movement is magnified to drive an indicator pointer. The Bourdon tube can be manufactured to indicate high or low pressures, but it's normally associated with higher pressures such as engine oil pressure. As well as the actual pressures, warnings can be displayed to the pilot by pressure-operated switches. These switches can operate for low, high, or incorrect differential pressure. A differential switch or gauge is subjected to pressure on both sides of its sensor. In many of the systems associated with the operation of the aircraft and its engines, liquids and gases are used, the pressures of which must be measured and indicated. The gauges and indicating systems fall into two categories: direct reading and remote indicating. A remote indicating system uses a remotely positioned sensing element, which is connected to the pressure source. The sensing element translates the actual pressure reading into an electrical signal. The sensing element then sends the signal via electrical wiring from its remote position to an instrument in the cockpit. A direct reading pressure instrument is physically connected to the source of the pressure that it's sensing. For instance, a direct reading engine oil pressure gauge will be connected via an oil pressure pipeline directly to the engine, to the point where the oil pressure is to be measured. Coloured arcs of green, amber, or red are used to indicate the range and limits of the pressure system. Vibration monitoring equipment is fitted to almost all commercial jet engine aircraft. Although gas turbine engines have an extremely low vibration level, any change in that level is usually indicative of damage which may lead to failure. Warnings will be given in the cockpit if the vibration levels are exceeded, and some systems have a continuous readout of vibration levels. Modern engines have the facility whereby the vibration level of each rotating assembly can be monitored, so that the source of any vibration can be pinpointed. The principle upon which vibration monitoring equipment works requires an input from a detector, which can be either a piezoelectrical crystal mounted strategically on the engine, or a fixed coil carrying 115 volts at 400 Hz, the output of which will be affected by the movement of a magnet within it, which is mounted on springs. In either case, the frequency of the incoming vibrations will be amplified, and then filtered so that only those frequencies that are indicative of damage occurring to the engine will affect the output. The output of the detector will affect the current flowing through the coil into the amplifier and filter. The filter will erase any output which is normal to the engine, but allow through to the amplifier any frequency that's considered to be harmful to the engine. The result of this amplification is sent to the instrument via the rectifier and warning circuit. The needle will show the appropriate deflection for the amount of vibration being suffered by the engine at that time. If the level of vibration exceeds a predetermined amount, a warning light on the instrument illuminates. Vibration is measured and displayed in relative amplitude. There are two methods of indicating the quantity of fuel carried in an aircraft. Either the volume, for example gallons, or the mass, kilograms or pounds, are measured. Because the mass of the fuel on board is of more interest to the pilot of a large aircraft than is the volume of the fuel on board, measurement of the volume of fuel is now only used on light aircraft. The simplest form of volume indication is a float system. Early aircraft used a float which sat on the surface of the fuel in the tank. Attached to the float was a piece of wire that protruded out of the top of the fuel tank. As the fuel level reduced, so the wire disappeared from view. A later system used the float to reposition a wiper on a variable resistor. This varied the current flowing to an indicator which had a pointer that moved over a scale calibrated in volume. The system was powered by direct current. The disadvantage of the float system is that the indication is not linear, and there is no provision for making adjustments for system accuracy. The gauge is set to be accurate at the low and empty positions. The system is also subject to errors caused by temperature changes, aircraft attitude changes, and aircraft acceleration. In its basic form, a capacitance system, which is much more accurate than the float system, consists of a tank unit, which is effectively a variable capacitor, located in the fuel tank, together with an amplifier and an indicator. A tank unit consists of two concentric aluminium alloyed tubes, which are held apart by pairs of insulating pins. The coaxial electrical connections are insulated, and the unit is insulated from the tank. The principle of operation of the capacitance system is based on the use of fuel and air as the dielectric between parallel plate capacitors, which have a fixed area and a fixed distance between them. The only variable in the system is then the ratio of the dielectrics used, which are fuel and air. That ratio is determined by the quantity of fuel in the tank. Incorporated in the system are reference units, which reduce indication errors that would occur if the dielectric constant of the fuel changes from its normal value, which is about twice that of air, and directly proportional to its density. Reference units are located on the lower end of a tank unit, and are always totally submerged in the unusable fuel that remains in the tank. The circuit is compensated for changes in temperature, and will indicate the mass of the fuel in the tanks. Fuel gauging systems can incorporate an additional indicator known as the fuel totalizer, which can indicate the sum of all of the tank quantities. In the event of a gauge failure, the fuel gauging system will fail safe and drive the needle of the failed indicator slowly to the 0 position. A test circuit is incorporated which will simulate gauge failure. Place your cursor over the test button to activate the test. When the test switch is released, the pointer should return to its original position. If water is present in the fuel, it can cause errors in the indicating system. If the percentage of water is very large, the capacitors in the sensing units can be effectively shorted out. If this happens, the indicator needle will be driven beyond full scale. As well as the quantity of fuel measured, the instantaneous fuel flow can be shown. To obtain the indication of total fuel used, the instantaneous fuel flow must be integrated. The fuel flow meter can display either volume flow or mass flow. To indicate mass flow, the meter must be compensated for the density of the fuel. A fuel pressure gauge can be adapted to be used as a simple flow meter. This system is used on many light piston engine injection systems. Most gas turbine engines use an electrical sensor, which utilizes the change in either the torque output or the rotational speed of an impeller situated in the high-pressure fuel line to the fuel spray nozzles. This type of fuel flow meter consists of a cylindrical light alloy casting, within which are guide vanes that support the shaft of a helical vane impeller. The impeller has a magnet embedded in it. Electrical pick-off coils are situated in the wall of the cylinder casting. When the fuel flow rotates the impeller, a sinusoidal signal is induced in the pick-off coils. The frequency of the sinusoidal signal is proportional to the speed of the rotor, which in turn is proportional to the rate of flow. The total consumption is obtained by integrating the rate of fuel consumption over time. A flow meter that displays fuel consumed as well as fuel flow is called an integrated flow meter. Modern aircraft employ remote indicating systems that can be powered by either direct current or alternating current supplies. Whatever the power source, each data transmission system employs a remotely positioned transmitter located at the source of the information, and a receiver which responds to the information received. The DESIN transmission system is a simple transmission system with low torque characteristics, which is used for the remote indication of angular position. It's often used where a simple pointer and scale is adequate, for example, remote indication of flap, rudder and elevator positions, or to repeat the reading of an instrument at a remote point. The accuracy of the system is approximately plus or minus 2%. The transmitter consists of a continuous resistance ring or potentiometer, which has 3 fixed tappings, A, B and C, spaced 120 degrees apart, which are connected to the receiver. The input shaft carries 2 diametrically opposed spring-loaded sliding contacts, or wipers, which are in contact with the potentiometer. The wipers are fed via slip rings and brushes with direct current. The receiver consists of 3 high-resistance coils, whose axes are spaced 120 degrees apart, with a permanent magnet rotor pivoted at their center carrying a pointer shaft. The 3 coils are connected to the tapping points A, B and C in the transmitter. When direct current is applied to the transmitter wipers, the voltages at the tapping points A, B and C produce a current flow in the 3 stators of the receiver, and a resultant magnetic field is produced. The rotor magnet aligns itself with this magnetic field. The magnitude and polarity of each tapping point voltage varies according to the position of the wipers, and thus, if the input shaft is rotated, the change of voltages at A, B and C produces a variation in the current flowing in the stator coils, and rotation of the resultant magnetic field in sympathy with the rotation of the input shaft. The rotor magnet remains aligned with this field at all times, and so rotates in synchronism with the input shaft. Here the voltage distribution around the potentiometer is such that point A is at plus 24 volts, while points B and C are both at plus 8 volts. Because the voltage at A differs from that at B and C by the same amount, current flows from A through coil A in the receiver, then divides equally at the start point, with half the total current flowing through coil B and half through coil C back to the transmitter. The resultant magnetic field in the receiver, with which the rotor magnet aligns itself, is compounded from the vectors representing the individual fields. If the input shaft is rotated through 120 degrees in a clockwise direction, as shown here, the voltage distribution around the potentiometer is such that the current flows from B through coil B in the receiver, then divides equally to flow through coils A and C back to the transmitter. The vectors show that the resultant magnetic field also rotates through 120 degrees clockwise, and the rotor shaft aligns itself along this new axis. Thus, if the wipers in the transmitter are placed in any position by the input shaft, the resultant field at the receiver, and hence the rotor magnet, takes up a corresponding position. If a pointer moving over a calibrated scale is attached to the rotor, remote indication of the position of the input shaft is immediately available. The DESIN system has inherent errors caused by the wiper arm being in physical contact with the potentiometer. This causes inaccuracies due to friction and carbon contamination of the resistor. The Celsin was developed in 1925. Halfway through the Second World War, the Americans reinvented the Celsin and caused it the Synchro. The Celsin is a system whereby a transmitter and a receiver, powered by alternating current, are electrically connected so that angular rotation of the rotor in the transmitter is reproduced simultaneously in the receiver. The transmitter consists of a stator and a rotor. The stator has 3 electrical coils whose axes are 120 degrees apart. The 3 stator coils are star connected. The rotor is mounted on a shaft and has 1 electrical winding, the 2 ends of which terminate in 2 slip rings. Carbon brushes feed power to the rotor through the 2 slip rings. The receiver is identical to the transmitter, and they are connected electrically to each other as shown here. The 2 rotors are supplied by alternating current from the same source. With power applied, both of the rotors will adopt the same position relative to their stators. The rotor of the transmitter can be attached to the output shaft of any device which needs positional information communicating to a remote position. The magnetic flux generated in the coil of the rotor interacts with the coils of the stator and causes a current to flow in their windings. Because the stator coils of the transmitter and receiver are in series with each other, the stator coils of the receiver now have a magnetic field around them which is identical to that around the stator coils in the transmitter. The rotor in the receiver aligns itself with the magnetic field which is formed in the receiver stator, adopting a position which is identical to that of the transmitter stator. The synchro system is more accurate than the DESIN system. Some aircraft indicate and record usage of their engines in flight. The flight hour meter can be coupled to an airborne sensor which energizes it at certain airspeeds. The information obtained from the flight hour meter can be used to determine the time to run between engine servicing periods. The display of the parameters associated with engine performance and airframe systems control by means of cathode ray tube type display units has, like those of flight instrument systems, become a standard feature of many types of aircraft. The display units form part of 2 principal systems, called the Engine Indicating and Crew Alerting System, ICAS, and Electronic Centralized Aircraft Monitoring, ECAM system. These systems were first introduced in Boeing 757 and 767 aircraft and the Airbus A310 respectively. As far as ICAS is concerned, engine operating data is displayed on its cathode ray tube units, thereby eliminating the need for traditional engine instruments. Engine operating data, as well as that relevant to other systems, is not necessarily always on display. But in the event of malfunctions occurring at any time, the flight crew's attention is drawn to them by an automatic display of messages in appropriate colors. However, in the Airbus A310, in which system operation was displayed in checklist and schematic form, the early ECAM concept was based on the view that engine data needed to be displayed during the whole of a flight, and accordingly traditional engine instruments were retained. It's of interest to note, however, that in subsequent types produced by this manufacturer, for example the A320, the ECAM system is developed to include the display of engine data in one of its display units. The basic ICAS system comprises two display units, a control panel which is called the Display Select panel, and two computers which are supplied with analog and digital signals from engine and system sensors. The computers are designated left and right, and only one is in control at a time. The other is on standby, and in the event of failure, it may be switched in either automatically or manually. Operating in conjunction with the ICAS system are discrete caution and warning lights, which are situated on the front coaming, a standby engine indicator panel, and a remotely located panel for selecting maintenance data displays. The system provides the flight crew with constantly displayed information on primary engine parameters and with secondary engine parameters and advisory, caution, warning alert messages displayed as required. The display units provide a wide variety of information relevant to engine operation and operation of other automated systems, and they utilize color cathode ray tubes. The units are mounted one above the other. The upper unit displays the primary engine parameters, N1 speed, exhaust gas temperature, and warning and caution messages. In some cases, this unit can also display the engine pressure ratio, depending on the type of engines installed and on the methods used to process data by the thrust management control system. The lower unit displays secondary engine parameters, that is N2 speed, fuel flow, oil quantity, pressure and temperature, and engine vibration. In addition, the status of non-engine systems, for example, flight control surface positions, hydraulic systems, the auxiliary power unit, etc., can also be displayed, together with aircraft configuration and maintenance data. The row of V's shown on the upper display unit only appears when secondary information is being displayed on the lower unit. 7 colors are produced by the cathode ray tubes, and they are used as follows. White, all scales, normal operating range of pointers, digital readouts. Red, warning messages, maximum operating limit marks on scales, and digital readouts. Green, thrust mode readout and selected EPA and N1 speed marks or target cursors. Blue, system testing only. Yellow, caution and advisory messages, caution limit marks on scales, digital readouts. Magenta, during in-flight engine starting and for cross-bleed messages. Cyan, names of all parameters being measured, for example, N1, oil pressure, TAT, etc., and status marks or cues. ICAS is designed to categorize displays and alerts according to function and usage, and for this purpose there are three modes of displaying information: 1. Operational, 2. Status, and 3. Maintenance. Operational and status modes are selected by the flight crew on the Display Select panel, while the maintenance mode is selected on the maintenance panel, which is for the use of ground engineering staff only. The operational mode displays the engine operating information and any alerts which are required to be actioned by the crew. Normally, only the upper display unit presents information. The lower one remains blank, but it can be selected to display secondary information as and when required by pressing the Engine button on the Display Select panel. Use your mouse to press the Engine button on the Display Select panel to see secondary information being shown on the bottom screen. When selected by pressing the Status button on the Display Select panel, the Status mode allows data to be displayed on the bottom screen, which is used to determine the dispatch readiness of an aircraft. This data is closely associated with details contained in the aircraft's minimum equipment list. The display on the bottom screen shows positions of the flight control surfaces in the form of pointers registered against vertical scales, selected subsystem parameters, and equipment status messages. Selection is normally done on the ground, either as part of the pre-flight checks of dispatch items or prior to shutdown of electrical power to aid the flight crew in making entries in the aircraft's technical log. Use your mouse to press the Engine and Status buttons on the Display Select panel to change the information shown on the bottom display between engine secondary information and the status display. The Maintenance mode provides maintenance engineers with information in 5 different display formats to aid them in troubleshooting and verification testing of the major subsystems. This display shows an example of the ECS MSG maintenance page on the bottom screen. The top screen displays data in a compact format. This display shows an example of the electrical hydraulic maintenance page. The displays, which are presented on the lower display unit, are not available in flight. The Display Select panel permits control of ICAS functions and displays, and can be used both in flight and on the ground. It's located on the center pedestal on the aircraft flight deck. Moving your mouse cursor over each control will display the purpose of each of them. The system continuously monitors a large number of inputs, typically over 400 from engine and airframe system sensors, and will detect any malfunctioning of systems. If any malfunction should occur, then appropriate messages are generated and displayed on the upper display unit in a sequence corresponding to the level of urgency of action to be taken. Up to 11 messages can be displayed on the top line at the left of the display screen and at the following levels. Level A. Warning requiring immediate corrective action. Level A warnings are displayed in red. Master warning lights are also illuminated, and aural warnings, for example the fire bell, from a central warning system are given. Level B. Cautions requiring immediate crew awareness and possible action. These are displayed in amber, and also by message caution lights. There is also an aural tone which is repeated twice. Level C. Advisories requiring crew awareness. Advisories are also displayed in amber. No caution lights or aural tones are associated with this level. In order to differentiate between a caution and an advisory, the latter is always indented one space to the right. When a new fault occurs, its associated message is inserted on the appropriate line of the display. The occurrence of a new fault may cause older messages to move down one line. For example, a new warning message would cause all existing warning, caution, and advisory messages to move down one line. A message is automatically removed from the display when the associated condition no longer exists. In this case, messages which appear below the deleted one each move up a line. If there are more messages than can be displayed at one time, the whole list forms what is termed a page, and the lowest message is removed, and a page number appears in white on the lower right side of the list. If there is an additional page of messages, it can be displayed by pushing the Cancel switch on the ICAS Caution and Annunciator panel. We'll show the ICAS Caution and Annunciator panel shortly. Warning messages are carried over from the previous page. The captain and first officer each have a dual-purpose warning caution light on their side of the glare shield. Part of the ICAS Caution and Annunciator panel is used to position cancel switches and a recall switch. Pushing the cancel switch removes only the caution and advisory messages from the display. The warning messages cannot be cancelled. Moving your mouse cursor over each control or indicator will display their purpose. If the lower display unit should fail when secondary information is being displayed on it, an amber alert message appears at the top left of the upper display unit, and the information is transferred to it as shown here. The format of this display is referred to as compact, and it may be removed by pressing the Engine switch on the Display Select panel. Failure of a display unit causes the function of the status switch on the Display Select panel to be inhibited, so that the status page format cannot be displayed. If the Display Select panel fails, the advisory message ICAS Control panel appears at the top left of the upper display unit, together with the primary information, and the secondary information automatically appears on the lower display unit. The cancel recall switches do not operate in this failure condition. The standby engine indicator provides primary engine information in the event that a total loss of ICAS display occurs. The information shown on the standby engine indicator relates to N1 and N2 speeds, EPA and EGT, and the displays are of the LCD type. Operating limit values are also displayed. Moving your mouse cursor over each part of the indicator will display the purpose of it. The Maintenance Control Panel is for use by maintenance engineers for the purpose of displaying maintenance data which is stored in system computer memory during flight or ground operations. Moving your mouse cursor over each control or indicator will display its purpose. The units that comprise the ECAM system, as it was originally developed for the Airbus A310, are shown in this functional diagram. As far as the processing and display of information are concerned, the ECAM system differs significantly from ICAS, in that the displayed data relates essentially to the primary systems of the aircraft, and is shown in checklist and pictorial or synoptic format. Engine operating data is displayed by conventional types of instruments. Other differences between the ICAS and the ECAM systems relate to display locations and methods of selection of system operating modes. The display units are mounted side by side in the early version of the A310. The left-hand unit is dedicated to information on the status of systems, warnings, and corrective action in a sequenced checklist format, while the right-hand unit is dedicated to associated information in pictorial or synoptic format. In this example, both the names and the symbols of unlocked doors are shown in amber. The symbols of locked doors are shown in green, while their names are in white font. There are 4 display modes, 3 of which are automatically selected. The first is referred to as flight phase related. The second is the advisory mode and status. The third mode is failure related. The fourth mode is selected manually and called the aircraft system display. In normal operation, the flight phase related mode automatically displays graphics appropriate to the current phase of aircraft operation. Those phases could be pre-flight, takeoff, climb, cruise, descent, approach, or after landing. In this example of the pre-flight phase, the left-hand display unit displays an advisory memo mode, and the right-hand unit displays a diagram of the aircraft's fuselage, doors, and arming of the escape slides deployment system. Status messages, which are also displayed on the left-hand display unit, provide the flight crew with an operational summary of the aircraft's condition, possible downgrading of auto-land capability, and, as far as possible, indications of the aircraft status following all failures except those that do not affect the flight. This example of an advisory display shows any aircraft limitations caused by the condition of the aircraft in blue font. Any systems or system functions which have been lost or affected in yellow font, and any further information deemed to be useful in white. The failure-related mode takes precedence over the other 2 automatic modes and the manual mode. In this example of a failure-related mode display, while taxiing out for takeoff, the temperature of the brake unit on the rear right wheel of the left main landing gear bogie has become excessive. A diagram of the wheel brake system is immediately displayed on the right display unit, and simultaneously the left unit displays the corrective action to be taken by the flight crew. As the corrective action is carried out, the instructions on the left-hand display are replaced by a message in white confirming the result of the action. The diagram on the right-hand display unit is appropriately redrawn as its system parameters change. In this example, the failure-related mode warning relates to a single system, and by convention, such warnings are signified by underlying the system title displayed. In cases where a failure can affect other subsystems, the title of the subsystem is shown boxed, as is shown in this example. Warnings and the associated lights are cleared by means of clear push-button switches on the ECAM control panel. The aircraft system display mode permits the selection of diagrams related to any one of 11 of the aircraft systems for routine checking, and also the selection of status messages, provided no warnings have been triggered for display. The selections that determine which systems are displayed are made by means of illuminated push-button switches on the system control panel. The layout of the ECAM control panel is shown here. All of the switches, with the exception of those for display control, are of the push-button illuminated caption type. Moving your mouse cursor over each control or indicator will display its purpose. This concludes the Engine Instruments lesson. In this lesson, you'll learn about propellers, their function, and operation. Although we will, of necessity, very occasionally make mention of the aerodynamics of propellers, it is important you be aware that this is not a lesson on the aerodynamics of propellers. Propeller aerodynamics are dealt with in the subject Principles of Flight. The purpose of a propeller is to provide thrust to drive the aircraft forwards through the air. This is achieved by accelerating a comparatively large mass of air rearwards, thereby producing forward thrust. A propeller consists of two or more aerodynamically shaped blades attached to a central hub. This hub is mounted onto a propeller shaft which is driven, either directly or indirectly, by the engine. The hub and the blades are thus spun round by the propeller shaft, and act rather like wings, which by rotating would generate lift, or in this case, thrust. In order to be able to explain how a propeller works, it's necessary that we use a certain amount of terminology. Like a wing, a propeller blade has a root and a tip, a leading and trailing edge, and a cambered cross-section, whose chord line passes from the center of the leading edge radius to the trailing edge. The cambered side of the blade is called the back, while the undercambered side is termed the thrust face. Where the section of the blade becomes round at the root area is termed the blade shank, while the base of the blade is called the blade butt. The propeller blade is set into its hub so that its chord line forms an angle with the plane of rotation of the whole propeller. This is called either the pitch or blade angle. The theoretical distance, ignoring slippage, that a propeller or propeller blade moves forwards when the propeller shaft has completed one rotation is called the geometric pitch. All propellers, however, lose a certain amount of efficiency due to aerodynamic and compressibility losses. As a result, the geometric pitch can never be achieved. The actual distance that the propeller moves forward during one revolution is called the effective pitch. The efficiency loss, that is, the difference between geometric pitch and effective pitch, is known as slip. The efficiency achieved will usually be in the range of 80 to 90%, and can be found by using this formula. The path of the propeller blade through the air, which describes a helix, determines the direction from which it will receive its relative airflow. This helical path is the resultant of the propeller blade rotational velocity and the aircraft forward velocity. The angle between the relative airflow, the actual path the blade describes through the air, and the chord line of the blade is called the angle of attack. The angle of attack is kept quite small, usually between 2 to 4 degrees. As the blade rotates at this small, positive angle of attack, a thrust force is generated, very similar to the way in which lift is generated on a wing. Because the rotational velocity of any point on a propeller blade increases with increasing distance from the center of the hub, so the magnitude of the thrust generated at any point along the blade would also increase with this distance, if the pitch of the blade remained constant along its entire length. If the blade pitch remained constant along the length of the propeller blade, the increase in force developed by the outer part of the blade, compared with that developed at the slower moving blade root, would tend to bend the blade as depicted here. The angle of attack depends on blade angle, the rotational speed of the propeller, and the forward speed of the aircraft. To keep the angle of attack within necessary limits along the length of the blade, we therefore reduce the blade pitch from root to tip. This has the effect, when the aircraft is in flight, with the propeller rotating at its designed operating RPM, of maintaining a fairly constant thrust force along the length of the blade. We've just seen that a propeller receives its relative airflow from a direction which is governed by the aircraft's true airspeed in the direction of flight, and its own rotational velocity in the plane of rotation. The operating angle of attack will be the angle between the relative airflow and the chord line of the propeller blade. This chord line is set at an angle to the plane of rotation, which, as we've already seen, forms the blade angle or the propeller pitch. From this animation, it can be seen that an increase in true airspeed will reduce the angle of attack. whereas an increase in rotational velocity, or RPM, will increase it. At high true airspeed and low propeller RPM, for instance with the aircraft in a power-off dive, it's possible to reduce the angle of attack to 0. While at low true airspeed and high RPM, for instance in the climb, it's possible to stall the propeller blade. Both extremes are obviously inefficient and therefore undesirable. The conclusion that must be drawn is that for a given fixed pitch, a propeller will only work efficiently at one combination of true airspeed and RPM, as is shown in this diagram. The propeller designer will attempt to ensure that peak efficiency is achieved at cruise true airspeed and cruise RPM. When a fixed-pitch propeller is being driven by a piston engine, the RPM is dependent on both the power setting, throttle position, selected by the pilot, and the true airspeed of the aircraft. It would be possible to overspeed the engine in a dive if the throttle was not closed. Conversely, with the aircraft stationary on the ground, it may not be possible to achieve rated RPM with the throttle fully open. Because of all of the disadvantages of the fixed-pitch propeller that we have just mentioned, advanced piston engine aircraft are fitted with variable pitch, constant speed propellers. This type of propeller is able to operate efficiently over a wide range of airspeeds. The power setting of a piston engine is defined by a combination of manifold pressure and engine RPM. Where both a separate power lever and a propeller RPM control are provided, it's possible to vary one of these parameters while leaving the other to remain constant, so optimizing the operation of the engine-propeller combination to give the best efficiency and fuel economy, while reducing the engine wear and tear to a minimum. In order to achieve this, a variable pitch propeller is used. The system changes the pitch angle of the propeller blade to vary the load on the engine, thereby maintaining the selected RPM of the engine-propeller combination independent of manifold pressure, provided that the propeller is operating between its fine and coarse pitch stops. The fine and coarse pitch stops may be fitted internally or externally, depending on the make of the propeller. Once an RPM has been selected, a control unit, either a constant speed unit or propeller control unit, will automatically vary the propeller blade pitch angle, and therefore its angle of attack to the prevailing relative airflow, in order to maintain the selected RPM despite variations in airspeed and manifold pressure. Variable pitch propellers may also have a reverse pitch and/or feathering function, the advantages of which will be discussed later in this lesson. This animation shows that under normal propeller control conditions, it's possible to provide a range of propeller pitch angles ranging from max coarse, cruise, all the way through to reverse pitch. The alpha, or constant speed range, is used for normal flight. It includes all pitch angles from flight fine through to max coarse, while the beta, or ground range, includes pitch angles between flight fine and maximum reverse. The feather position is not included in either range, and is used for emergency conditions only. In the event of engine failure, the propeller blades will be moved directly to this position to prevent windmilling. There are no pitch angles available between max coarse and feather. The method of control within the alpha and beta ranges, and the means of achieving the propeller feather position, will be discussed progressively throughout this lesson. Varying the pitch of a propeller throws up two basic problems, one of blade actuation and one of pitch control. We will initially examine the problem of blade actuation. The issue of pitch control will be covered later in this lesson. Although mechanically or electrically actuated pitch change mechanisms are in use, the hydraulic method is the most commonly used. The system utilizes oil from the engine or reduction gearbox lubrication system as the source of hydraulic pressure. In this system, the pitch change mechanism is operated by a piston moving under the influence of the oil pressure. Use the up and down arrows on your keyboard to change the pitch of the blades on this propeller. Hydraulic pitch change mechanisms can be one of two types, single-acting or double-acting. A single-acting propeller has oil pressure applied to only one side of the piston. The return movement of the piston requires the force of a spring, or sometimes compressed gas. A double-acting propeller has oil pressure applied to either side of the piston, in order to move the propeller between the two extremes of fine and coarse pitch. Whichever type is used, the flow of oil to and from the actuating piston is controlled by a propeller governor. Dependent on the propeller manufacturer, the governor may also be known as a constant speed unit or propeller control unit. In addition to controlling the propeller pitch angle, the unit normally incorporates a small oil pump, which increases the oil pressure to the value required for system operation. A single-acting propeller is constructed basically like any other variable pitch propeller, in that the blades are arranged round a central, engine-driven hub with the cylindrical hydraulic pitch change mechanism mounted at the front. The pitch change cylinder, or dome, contains a movable piston which is activated by boosted engine oil pressure. Movement of the piston will rotate the propeller blades towards either coarse or fine pitch. Typically, rotation is accomplished by a mechanical linkage attached to the rear of the piston, which operates an actuating pin machined on the butt of each blade. The actuating pin is offset, in order that it can impart the correct range of angular motion. Generally, blade rotation towards coarse pitch is induced by an internal spring or gas pressure, and or counterweights attached to the blade roots. Most single-acting propellers, however, will utilize both a spring and counterweights. As we said earlier, some systems may use compressed gas instead of the spring. In feathering-type propellers, the spring has a dual function. It assists the counterweights in driving the propeller blades towards coarse pitch, and, when selected by the pilot, it actuates the blades into the feathered position, when engine RPM is low and there is insufficient centrifugal force acting on the counterweights. The constant speed unit, or CSU, incorporates a valve, which, because it has lands or grooves cut into the operating portion of its stem, is called a landed valve. This landed valve controls the flow of oil to and from the propeller actuating, or pitch change cylinder. A speeder spring, acting above the valve, tends to force the valve downwards, while a set of flyweights, driven by the engine, oppose the spring and act to lift the valve. An input from the pilot's RPM lever, or propeller condition lever, will adjust the setting of the speeder spring, selecting the RPM, which the CSU then automatically maintains. In order that it can respond to the various demands made by the pilot regarding the propeller RPM, the constant speed unit controls the oil flow to the pitch change cylinder in three ways. If the propeller is underspeeding, then the flyweights will be leaning inwards because of the reduced centrifugal force, allowing the speeder spring to push the landed valve downwards. This will allow the unit to supply oil to fine off the pitch of the propeller, causing an RPM increase. If the RPM is as required, in other words the propeller is on speed, then a hydraulic lock is formed in the system, maintaining the blade pitch constant. If the propeller is overspeeding, then the flyweights will be forced outwards by centrifugal force, compressing the speeder spring and allowing the landed valve to move upwards. This will allow oil to drain back into the engine system as the piston is moved under the force of the spring, coarsening the blade pitch, causing an RPM decrease. One type of double-acting mechanism used on larger propellers, like the one shown here, achieves control of blade pitch angle by means of a hydraulically actuated piston, connected to a cam slot, which rotates a bevel gear. The bevel gear engages with and drives other bevel gears located at the butt of each blade. Oil flow to either side of the piston is controlled by a propeller control unit. Alternatively, the type of control system shown here has a similar pitch change mechanism to the single-acting propeller. Like the single-acting propeller, its pitch change mechanism is also mounted towards the front of the hub, and the cylinder also contains a hydraulic piston. However, in the double-acting system, this piston will have hydraulic pressure directed to either side of it. Fine pitch oil is sent to one side of the piston, or coarse pitch oil is sent to the other. This eliminates the need for coarse pitch springs or gas pressure, and, with the exception of some larger propellers, the assistance of centrifugal counterweights. The double-acting propeller's controller will respond to the various demands made by the pilot regarding the propeller RPM to control the oil flow to either side of the piston in the pitch change cylinder in three ways. If the propeller is underspeeding, then the flyweights will be leaning inwards because of the reduced centrifugal force, allowing the speeder spring to push the landed valve downwards. This will allow the unit to supply oil to fine off the pitch of the propeller, while simultaneously porting coarse oil to return. The piston will move to fine off the blades, causing an RPM increase. If the RPM is as required, in other words the propeller is on speed, then a hydraulic lock is formed which traps oil both sides of the piston, maintaining the blade pitch constant. If the propeller is overspeeding, then the flyweights will be forced outwards by centrifugal force, compressing the speeder spring and allowing the landed valve to move upwards. This will simultaneously allow coarse oil to be ported to one side of the piston and fine oil to drain back into the engine from the other side. The piston will move to coarsen the blade pitch, causing a decrease in RPM. A constant speed propeller must be capable of all the pitch change operations mentioned previously, as they are selected by the pilot moving the RPM lever in the cockpit. The system must also be capable of maintaining a selected RPM within its own operational limits, regardless of changes in airspeed, altitude, and engine power setting. When the constant speed unit senses that the RPM is as has been selected, the system remains in a static state. However, any change in airspeed, altitude, or engine power setting will result in a tendency to either increase RPM above or decrease RPM below the value selected. As we've seen already, a tendency for RPM to increase, an overspeed condition, will be countered by a supply of oil being fed to the coarse pitch side of the piston in the pitch change mechanism. As is shown in this animation, the pitch will then coarsen and propeller torque will rise as a result of the increase in the blade angle of attack. Propeller torque now exceeds the engine torque and will cause the RPM to decrease back to the selected setting. As the RPM regains its previously selected value, the movement of the landed valve in the constant speed unit, which directed the oil flow in the first place, is progressively reversed until it regains the sensitive position, where a hydraulic lock holds the position in the pitch change mechanism immovable until the next RPM selection or disturbance in airspeed, altitude, or engine power setting. A tendency for the RPM to reduce, which is termed a propeller underspeed condition, must be countered by a supply of oil being fed to the fine pitch side of the piston in the pitch change mechanism. As is shown in this animation, the pitch will then fine off and propeller torque will fall as a result of the decrease in the blade angle of attack. Propeller torque is now less than the engine torque and will cause RPM to increase back to the selected setting. As RPM regains its previously selected value, the movement of the landed valve in the constant speed unit, which directed the oil flow in the first place, is progressively reversed until it regains the sensitive position, where a hydraulic lock holds the piston immovable until the next RPM selection or disturbance in airspeed, altitude, or engine power setting. Should an engine fail in flight, its propeller control unit would sense a drop in RPM, and, in an attempt to maintain the pilot's selected RPM level, would move to the underspeed or fine pitch position. Centrifugal moments acting on the blade would cause it to rotate towards fine pitch. This would result in the propeller being put into a windmilling situation, with its pitch change piston abutting the fine pitch stop. The immediate result of this would be a very large asymmetric drag, which would yaw the aircraft violently towards the failed engine. A second possibility, if the propeller continued to windmill and drive the engine, could be a complete mechanical breakdown of the engine, and even an engine fire. So, to minimize drag, and also to prevent further possible damage to the engine and the aircraft, some propellers, particularly on multi-engine aircraft, are provided with a means of turning the blades edge-on to the air flowing over them. In this edge-on position, where no aerodynamic force is generated either forwards or backwards, the propeller will cease to rotate. This action is called feathering the propeller. If the engine had actually failed, there would be no requirement to unfeather its propeller. However, propeller manufacturers usually provide an unfeathering facility, by means of which, if appropriate, an engine restart may be attempted. This may be a requirement following asymmetric flight practice. The operating principle of the propeller control unit incorporated in a feathering propeller is similar to that previously discussed, in that the unit contains an oil pump to boost oil pressure delivered from the engine or reduction gearbox, and a hydromechanical governor for RPM control. There is, however, the addition of a feathering mechanism, the operation of which will be discussed progressively throughout the lesson. Control units with feathering mechanisms may be found on both turboprop or reciprocating aero engines. Dependent on the manufacturer and type of propeller system, the controller may be known as a propeller governor, a constant speed unit, CSU, or a propeller control unit, PCU. For the remainder of this lesson, we'll refer to the unit as the propeller control unit, or PCU. The controls available to the pilot are, again, dependent on type. Most spark ignition piston engines, and many turboprop engines, are equipped with a twin-lever cockpit arrangement, whereby the pilot has separate engine power and propeller control levers. In this arrangement, propeller feathering can be manually achieved by moving the propeller control lever to the feather position, or on some aircraft, by means of a separate feather lever. Some turboprop engines utilize a single lever arrangement, whereby the pilot is provided with a power lever only. In this arrangement, propeller pitch, RPM, and engine fuel flow, power, are simultaneously adjusted. Feathering may be achieved by moving the engine high-pressure fuel cock to the feather position. New generation reciprocating engines equipped with Full Authority Digital Engine Control, or FADEC, also use a single lever arrangement, whereby the pilot selects the required power setting and the propeller pitch angle is controlled either electronically by an electronic engine control unit or by a hydromechanical control unit. This diagram illustrates that the propeller control unit may contain a number of components which are additional to the basic constant speed system that we discussed earlier. The feathering mechanism provides a means of manually lifting the landed valve to the overspeed or coarse pitch condition when the appropriate control is moved to the feather position. The actions required to feather a propeller are dependent on the type of engine and propeller combination and the type of aircraft they are installed in. For single-acting propellers, this normally involves moving the propeller condition lever, or RPM lever, to the feather position. Moving the appropriate lever to the feather position mechanically lifts the landed valve against the speeder spring to its highest position, thereby simulating an exaggerated overspeed condition. the landed valve will remain in this position until the feathering control is moved back to its normal position. Any oil in the pitch change cylinder can now drain away, allowing the spring or gas pressure, assisted by counterweights, to move the piston onto the feathering stop. To unfeather the propeller, the speed of spring tension is released by moving the propeller control lever to a position comparable to that of the serviceable engine, which of course is running at normal operating RPM. This moves the landed valve down and connects the reserve oil pressure line to the fine pitch side of the propeller pitch change cylinder. A reserve of oil pressure may be supplied by means of an accumulator, which is charged continuously during normal operation. By activating a release valve, oil pressure from the accumulator is directed to move the pitch change piston to fine pitch. Alternatively, some systems may utilize an electrically operated unfeathering pump, or, on some smaller systems, the engine may require motoring over on the starter to build up sufficient oil pressure. Once the propeller blades have moved away from the feathered position, the propeller will start to windmill, and as long as the engine has fuel and ignition, it should start. When an engine, which is fitted with a single acting propeller, is shut down after flight, the propeller should be at the fully fine pitch position. There is a considerable quantity of oil trapped under pressure on the fine pitch side of the piston in the pitch change cylinder, which is holding the propeller in the fully fine position. This oil pressure is being opposed by the force of the feathering spring. After engine shutdown, the trapped pressure will gradually leak away past the landed valve in the constant speed unit. As this trapped hydraulic pressure leaks away, the feathering spring is able to slowly push the propeller blades towards the fully feathered position. While this condition would be acceptable to a turboprop with a free power turbine, it would result in an unacceptably high loading on the starter motor of a piston engine or direct coupled turboprop. So, to prevent the feathering spring pushing the blades all the way to the feathered position, on those engines where a feathered propeller would cause stress on startup, centrifugal latch pins are incorporated in the pitch change mechanism. The latch pins are held disengaged by centrifugal force while the engine is running. As the engine RPM reduces, small springs behind the latch pins overcome centrifugal force, and they are allowed into contact with the piston mechanism. Typically, the value of the RPM at which the latch pins become engaged is around 650 to 700. After engine shutdown, the latch pins engage with a groove in the piston mechanism, which locks the piston. This prevents it from being pushed beyond a predetermined blade angle, and further into the feathered position by the feathering spring. When the engine is started and RPM increases, centrifugal force will disengage the latch pins. Fine pitch oil will quickly build up and hold the propeller against the fine pitch stop. Note that if a propeller engine combination does have a centrifugal latch mechanism fitted, it may become impossible to feather the propeller of that engine once its RPM has fallen below the latch setting value. This is because once they are engaged, the latch pins can prevent the piston being moved any further by the feathering spring. It is thus extremely important to complete the feathering drill before the RPM decays below this figure. Double-acting propellers do not have springs or gas pressure to assist in changing propeller pitch. Thus, all of the actuation, both to fine and coarse pitch, must be hydraulic. Engine or reduction gearbox oil is once again used as the hydraulic medium for this purpose. The inset diagram of a dry sump oil tank, which you may remember was used previously in the lesson on engine lubrication, illustrates how a protected source of feathering oil is provided. The oil pressure required for feathering the propeller is generated by an electrically driven pump, which may be activated by a feathering button in the cockpit. With the exception of operating the feathering pump, the basic control selection for feathering the propeller remains the same. That is, selection of the propeller control or condition lever, operation of a separate feathering lever, or, on some turboprop systems, moving the HP fuel cock to the feather position. For the purposes of this lesson, we'll consider that we are feathering a propeller which has twin lever control. The propeller control lever is brought back through the fully course position to the feather position. Alternatively, where fitted, the propeller feathering lever is operated. This action lifts the landed valve in the propeller control unit upwards, thereby connecting the feathering pump oil line to the coarse pitch side of the pitch change piston, and allowing oil to drain from the fine pitch side of the pitch change piston. The feathering button in the cockpit is pushed in, energizing the feathering pump solenoid relay to supply the feathering pump. It also energizes the holding coil, which keeps the feathering button depressed for the time being. Feathering oil now passes through the ports of the landed valve, pushing the pitch change piston so that it moves into contact with the feathering stop. Oil pressure will now build up within the system, eventually operating a pressure-operated cutout switch, which will interrupt the supply to the feathering button hold-in coil. This causes the feathering button to release, which terminates the supply to the feathering pump solenoid relay, which in turn breaks the supply to the feathering pump. If the propeller is allowed to windmill, the forces generated will cause it to try to unfeather itself. Moving the propeller blades a few degrees below the feathered position will cause the propeller to rotate, and centrifugal turning moments will tend to move the blades towards a finer pitch. This will cause the propeller to rotate faster, until it comes under the control of the propeller control unit. The propeller control lever of the unit being unfeathered should be placed in line with that of the operating engine or engines, and, where fitted, the feathering lever should be reset. This allows the speeder spring to push the landed valve down. It also helps to minimize the yaw which will inevitably accompany the effect of unfeathering. Pressure oil can now be directed to one side of the pitch change mechanism to move the piston towards a finer pitch, and coarse pitch oil will be allowed to drain from the other side as it does so. The feathering button should now be pressed. This starts the feathering pump running, which will supply the pressure oil to the pitch change mechanism to move the blades away from the feathered position towards fine. Once the propeller starts windmilling, the feathering button should be pulled out. Pulling out the feathering button overcomes the holding coil. When the contacts of the feathering button are opened, they break the supply to the solenoid relay, the contacts of which are supplying the feathering pump. Thus the feathering pump stops. The rest of the restart drill is accomplished in accordance with the aircraft operating manual. To reduce the workload on the pilot in the event of an engine failure, some propellers are equipped with an auto-feather system. The system is normally active during takeoff and cruise conditions only. For example, on a turbojet engine, with the high-pressure fuel cock open and the power lever set to high power, a signal of low torque from the engine torque meter system will automatically feather the propeller. Should either of these conditions not be met, the auto-feather system will be rendered inactive. This diagram shows an auto-feather system installed on a typical double-acting propeller arrangement for a turboprop engine. It consists of an additional oil pressure line supplied from an electrically operated feathering pump to the underside of a valve lift piston in the feathering mechanism. Control over this oil pressure is provided by an electrically operated solenoid valve. In the event of an engine failure, and provided the engine controls are set to the high-power configuration, a low torque signal will complete the auto-feather circuit and energize the valve lift solenoid and feathering pump. This delivers an independent supply of feathering oil to the valve lift piston, which raises the landed valve to the coarse pitch position. The high-pressure oil supplied by the feathering pump is now fed to the coarse pitch side of the pitch change piston, pushing it onto the feathering stop. As the piston moves, it displaces the fine pitch oil to return. The feathering stop is fitted within the pitch change mechanism, the position of which allows the propeller blades to take up a position edge-on to the aircraft's airflow, where they will generate zero aerodynamic force in either direction. The propeller should not now windmill. The propeller control unit incorporates a flight fine pitch stop solenoid, which controls a supply of high-pressure oil to a flight fine pitch stop mechanism in the propeller pitch change cylinder. When the solenoid is energized, oil pressure is directed to withdraw the flight fine pitch stop, thereby allowing the pitch change piston to move below the flight fine position and into the beta range. When the solenoid is de-energized, oil pressure is removed, and the flight fine pitch stop is engaged by spring pressure. Use your mouse to press the repeat button, which will enable you to see the removal of the flight fine pitch stop again. Most turboprop engines are provided with a system of propeller control which is defined by alpha and beta ranges. The alpha range is used at high speed, during the takeoff run, in flight, and during the initial high-speed part of the landing rollout. The alpha range is selected by moving the engine power lever to a position at or above flight idle. The beta range is used on the ground only. It's selected during the landing roll by first removing the flight fine pitch stop, or FFPS, which was previously engaged to prevent the blades moving to ground fine pitch in flight, and then moving the engine power lever to a position below the flight idle position. On systems not equipped with a hydraulic flight fine pitch stop, the power lever is moved through a flight idle detent or gate. With the propeller blades functioning within the alpha range, their pitch is controlled automatically by the propeller control unit, whilst within the beta range their pitch is controlled by the operator's movement of the engine power lever. In most aircraft, the selection of the beta range is made by movement of the flight fine pitch stop, the FFPS lever. Alternatively, in some systems the selection can be made via the condition lever, that is the RPM lever, itself. A warning light, usually blue or amber, illuminates whenever the flight fine pitch stop is disengaged. Additionally, other warning lights may be provided, which illuminate whenever the propeller blades are moved below the flight fine pitch position, that is, into the beta range. While the aircraft is taxiing, there is insufficient RPM available to bring the propeller control unit on speed, and it's therefore unable to take control. Propeller RPM is controlled by movement of the engine power lever within its range below flight idle. As power is applied for takeoff, the flight fine pitch stop lever is forced into the flight position by the action of moving the power levers to the takeoff power position. The FFPS light and/or beta lights are extinguished. As the pitch of the blades coarsens to allow the propeller to absorb the increased torque being produced by the engine, the piston in the pitch change mechanism moves into the flight pitch range, or alpha range. This allows the flight fine pitch stop to engage under spring pressure, thereby preventing the piston from moving below the flight fine pitch position. There is now sufficient RPM available to bring the propeller control unit on speed and into a controlling condition. Many turboprop aircraft, and a few high-powered piston-engined aircraft, are provided with a means to allow the operator to select a superfine pitch, or to aerodynamically reverse the pitch of their propellers, or even in some cases to do both. In the case of a superfine pitch selection, a fixed abutment stop in the pitch change cylinder allows the piston to take up a position at or near 0 degrees. This is known as a disking position, and is used for starting and initial acceleration of the engine, and for aerodynamic braking during the landing roll. Superfine pitch is commonly called ground fine pitch, and its position is several degrees finer than the finest pitch available in flight, which is called flight fine pitch. The propellers of more modern aircraft may have a much greater range of blade movement in the beta range. The range can extend from around plus 8 degrees to minus 30 degrees pitch, which is full reverse. The beta range of this type of propeller is selected in a similar manner, and at the same point in the landing run as the previously discussed system, that is, during the high-speed initial part of the landing rollout. In this case, however, the braking effect obtained from the selection of reverse pitch is much more effective than that which would result from merely the selection of ground fine pitch. With the propeller in reverse pitch, the forces on the propeller blade are as shown here in the small diagram on the right of the screen. As you can see, in reverse pitch, the forces generated by the propeller will produce a braking effect to actively decelerate the aircraft after landing. On landing, the flight fine pitch stop lever must be moved to the disengaged or ground position before the engine power lever can be moved below flight idle. On systems not equipped with the removable flight fine pitch stop, the power lever must be moved through a fixed gate or detent. On some aircraft, microswitches, which sense that the weight of the aircraft is on the wheels, ensure that this selection cannot be made in the air. Once the power levers are moved below flight idle, the propeller blades move into the ground fine pitch range, and the propeller control unit relinquishes control. Propeller RPM is now controlled by power lever movement. The forward velocity of the initial landing roll, combined with low RPM and low blade angle, produces a zero or negative angle of attack. This reverses the total reaction produced by the propeller, which acts to slow the aircraft in its landing roll. This condition is known as disking braking. Propellers which can have their pitch angle made even more negative are known as fully reversing propellers. As the power lever is moved further rearwards into the reverse pitch range, the blades move into the negative pitch position. The reversed total reaction produced now increases. This exerts increased load on the engine, so engine power is increased in order to maintain a constant RPM. The engine power and reverse airflow through the propeller is now being used to slow the aircraft down. This condition is known as power-on braking. Many multi-engined aircraft are provided with a visual indicator, which is called a synchroscope, which indicates the RPM differences between the slave engines and the master. As you can see from this picture, the presentation consists of miniature propellers, which rotate to show when an RPM difference exists, and whether the slave is faster or slower than the master. In order to reduce the amount of vibration which can damage aircraft components, and also to reduce noise harmonics which can occur on propeller-driven aircraft, the engine propeller assemblies are often provided with a means of making the RPM of each unit the same as all the others. A synchronization system will reduce the annoying harmonics which can be produced by out-of-sync propellers, and also lower noise levels significantly. Electromagnets in the head of the rotating assemblies of the propeller control units of each engine are used to generate an RPM signal. An aircraft fitted with such a synchronization system will have a designated master engine, and other engines will be specified as slave engines. The signals from the propeller control unit of the master engine and those from the slave engines are sent to a control unit where they are compared. With the synchronizing system engaged, any RPM differences between the master and slave engines will be sensed in the control unit. The control unit generates proportional, positive or negative current outputs which are sent to torque motors. The torque motors are mounted on the slave engine propeller control units in such a way that a signal indicating that the slave engine is running at a lower RPM than the master will cause the slave engine's torque motor to turn in order to fire off its propeller, thus increasing its RPM until no discrepancy exists between the slave and master engine speeds. If, on the other hand, the control unit receives a signal indicating that a slave engine is running faster than the master engine, then it will send a signal to the appropriate torque motor to coarsen off the propeller blades of that slave engine to reduce its RPM, until once again no discrepancy exists between the slave and master engine speeds. So, the torque motor rotation resets the speeder spring on the affected slave engine's propeller control unit, which will ensure that it is once again synchronized with that of the master engine. When no difference in RPM exists between the master and the slave propeller, no output is sent to the slave torque motors. A more significant improvement in noise levels can be obtained by ensuring that adjacent propeller tips are separated by some optimum angle to prevent noisy interaction between them. This interaction is at a maximum when the propeller blade tips are opposite to each other, as is shown here. The synchronization system often also incorporates a synchrophasing feature that allows the operator to phase the propellers. Phasing is a means of adjusting the position of the blades on one propeller in relation to the blades of the one adjacent to it. The ability to phase can allow the operator to move much of the propeller vibration to unoccupied sections of the aircraft, thereby reducing the annoying beat of the propellers and providing additional comfort to the passengers. The systems of some aircraft provide the pilot with a means of manually fine-tuning this angle to obtain the quietest result. The more powerful an aircraft engine becomes, the larger must be its propeller if it's to absorb the torque output of that engine. Unfortunately, if the propeller diameter is increased as a way of increasing the size of the propeller, and the engine rotates at the same speed as it did previously, the propeller blade tips would be moving at sonic or even supersonic speed. This is very inefficient as well as being noisy and potentially damaging to the blades. So, if we have to use a large diameter propeller and yet maintain its RPM to a level that will not allow the tip speed to exceed that of the speed of sound, the propeller drive speed must be reduced to a more suitable level by a reduction gear, placed in the driveline between the engine and the propeller shaft, as is this example of a Pratt & Whitney R4360 engine, which is shown as a cutaway. The parallel spur gear type of reduction gear, whilst being mechanically simple and relatively cheap to produce, takes up a lot of room at the front of the engine. This is because the axes of the gears are parallel. This system of reduction gear has been utilized mostly on V-type, inline, water-cooled engines, for example the Rolls-Royce Merlin and Griffon engines. The epicyclic reduction gear layout is quite compact and has the advantage of being a concentric layout. All of the gears rotate about the same center line. The gears themselves may be straight cut, beveled, or even helically cut. Helically cut gears are extremely efficient in the way they transfer power, and they are also very smooth and quiet in operation. They do, however, impart a degree of end thrust which has to be contained, usually through the use of thrust bearings. This end or axial thrust is proportional to the torque passing through the shaft of the gear. Axial thrust, as we'll shortly see, can be used to provide a torque indication system in a propeller reduction system. A torque meter can be provided to give the pilot information about the amount of power the aircraft engines are generating during any phase of flight. The instrument may be calibrated in units such as pounds per square inch, pounds-feet, Newton meters, brake horsepower, or any other suitable unit of power. Either electronic or hydraulic torque meter systems can be found in service. An electronic torque meter system, such as the one shown here, utilizes the angular displacement of a driveshaft, which is placed between the engine and the propeller drive. This displacement, being proportional to the transmitted power, is measured electronically, and the signal thus generated is used to drive the needle in the torque meter. This system is inherently lighter and more reliable than the hydraulic system. There are two types of hydraulic torque meter system. One which utilizes the end thrust generated by a helically cut gear, the other employs the torque reaction of a ring gear. They are both used to alter the oil pressure of the torque transmission system, which is then transmitted to the torque meter gauge on the instrument panel. This simplified diagram shows a ring gear system. When the engine is running, the pinions or planet gears are being driven around inside the stationary gear by the central engine crankshaft. The thrust reaction generated by the rotation of the pinions will try to rotate the stationary gear in the opposite direction to that of the pinions. The stationary gear is restrained by being attached to pistons fitted within cylinders that are being supplied by oil pressure, which is generated by a torque meter system pump. One of the pistons in the system partially covers a bleed hole, which, if it's uncovered, will allow oil pressure to be dumped to the engine oil return. While the engine is running, the piston in the cylinder with the bleed orifice will take up a sensitive position where the oil pressure generated by the torque meter pump just balances the thrust being generated on the stationary gear. If the engine torque increases, the piston will be driven, by rotation of the stationary ring gear, to cover more of the bleed hole. This will cause the oil pressure within the cylinders to increase until the piston moves back into the sensitive position, where torque meter oil pressure once again balances engine torque. The increase in oil pressure required to achieve this balance is indicated on the torque meter gauge as a rise in engine output torque. If engine torque decreases, the oil pressure in the cylinders will now exceed the pressure required to balance the torque output of the engine, which is acting on the stationary ring gear. As a consequence, the pistons, which were being maintained in a sensitive position by the balance between the engine torque and oil pressure, will now move to uncover more of the bleed hole. This will cause the oil pressure to decrease until the piston moves back into the sensitive position, where torque meter oil pressure once again balances engine torque. The decrease in oil pressure required to achieve this balance is indicated on the torque meter gauge as a fall in engine output torque. Engine torque is proportional to the horsepower being produced by the engine, and this is transmitted through the propeller reduction gear. The helical gear torque meter system depends upon the axial thrust which is developed when helically cut gears are used to transmit power through the propeller reduction gear. The shafts of the gears rotate within cylinders, and the axial thrust they develop is balanced by oil pressure trapped inside the cylinders. Torque meter oil pressure is transmitted to a gauge in the cockpit. The gauge is calibrated in pounds per square inch. The system oil pressure, which in some systems can have quite a high value, for instance the Proteus engine was capable of developing about 800 pounds of torque, is generated by a torque meter system oil pump. In this system, which is similar to that used on the Rolls-Royce Dart engine, there is an oil pressure bleed hole within each cylinder. When the thrust developed by the helically cut gear is exactly balanced by torque meter oil pressure, the shaft of each helical gear takes up a sensitive position, partially covering the bleed hole. If engine power output increases, the axial thrust being transmitted by each gear also increases, which forces its shaft further into its retaining cylinder. Thus the shaft is forced into a new position where it blocks the bleed hole. The torque meter oil pressure, being unable to escape, now builds up to a new higher value, until it's able to force the gear shaft back into the sensitive position, where once again it's able to balance the axial thrust being developed by the helical gear. If the engine power output decreases, the axial thrust being transmitted by each gear also decreases, which allows its shaft to be displaced slightly out of the retaining cylinder. Thus the shaft is forced into a new position where it uncovers the bleed hole. The torque meter oil pressure now falls to a new, lower value, until the lower axial thrust being developed by the engine is able to overcome it and force the gear shaft back into the sensitive position in the cylinder. Once this has happened, axial thrust is again balanced by oil pressure in the cylinder, but now it's balanced by a lower torque meter value. In addition to giving an indication of engine power output, the torque meter system can also be utilized to send signals to the auto feather and the water methanol injection systems. The auto feather system, as its name implies, will automatically feather the propeller of a failed engine. This is particularly important if the failure occurs on takeoff. The checks to be carried out on a propeller after engine start and the methods used will vary from aircraft type to aircraft type and from propeller type to propeller type. In addition to the checks which are described here, it must be remembered that there are many other checks which are carried out on propellers. Most of these checks are maintenance orientated, but nevertheless a pilot is still responsible for the pre-flight visual inspection of the propeller. The particular checks that we are about to examine are those for the single-acting propeller fitted to the Piper PA-34-200T Seneca aircraft. After engine start, the engine oil must be warmed up to the level required by the operating manual before any checks are commenced. The checks form part of the normal after start and before takeoff checks. For the sake of minimizing confusion between gauges, we, in this demonstration, will concentrate only on the left or number 1 engine. The first check is a part of the power check. The remainder forms part of the before takeoff check. Here we've highlighted the particular parts of the checklist that we are concerned with. Throttle, 1900 RPM. Be aware that you don't really want to use any more RPM than necessary. Propeller, RPM lever. Exercise. This part of the check ensures that the propeller functions correctly under the impetus of the oil pressure being fed to the pitch control mechanism. Check. RPM drops when min RPM selected. Check. RPM drops when min RPM selected. Pull the propeller control lever to minimum and allow the RPM to decrease by 200. At this point, it's not necessary to wait until the RPM falls to the absolute lowest possible value. You're only checking for the correct functioning of the propeller control system. Check. RPM returns to 1900 when max RPM selected. Return the propeller control lever to maximum RPM and check that the RPM recovers back to 1900 as the propeller blades move back towards fine pitch. Repeat. Repeat the previous 2 checks again. By doing this, you'll ensure that warmer oil is being introduced into the propeller control mechanism and the associated pipework. The warmer oil will sharpen up the propeller's response to your movement of the propeller control lever. Throttle, 1500 RPM. Moving the propeller control lever back towards the white line on the control quadrant with this power set should not elicit any RPM change at all, because the propeller is within the constant speed range. Propeller feathering. Check. Moving the propeller control lever below the white line will cause the propeller blades to move towards the feathered position and the RPM to decrease. If, as is the case with the propeller we are considering, a centrifugal latch mechanism is fitted, it's important that the RPM should not drop below 1000, because the centrifugal latches will not become engaged and the propeller will feather, which is not what we're trying to achieve in this check. Throttle. Close and set 1200 RPM. Initially the throttle lever should be closed and the slow running RPM checked at between 7 to 800 RPM. Then the throttle should be set to obtain 1200 RPM. At this RPM the engine should run smoothly and the spark plug should not oil up while you're carrying out the checks on the other engine. Propellers. Max RPM. Select the propeller control lever to the maximum RPM position. Propeller de-icing. As required. If icing conditions expected during or immediately after takeoff, select On. Check propeller de-icing ammeter. Check both alternator ammeters. If your aircraft has double-acting propellers fitted, then the checks to be carried out are much the same as those for an aircraft fitted with single-acting propellers. There will, of course, be differences in detail concerning the basic RPM settings, etc., but the object of the checks will be the same. That is, to ensure a rapid and accurate response to RPM control lever movement. As with the single-acting propeller, it's necessary, once the lubricating oil in the engine has warmed sufficiently, to exercise the pitch change mechanism. This will evacuate the cold, sluggish oil from the pitch change cylinder and purge it from the constant speed unit and the associated oil passages. Just as happened with the Seneca checks, once the oil temperature is increased, there will be an engine test procedure for the double-acting propeller, which will involve causing the pitch change piston to travel from the fine pitch stop to the feathering stop more than once. With a double-acting propeller, there is not only double the amount of actuating oil in circulation, but also an extra system to check. The correct performance of the feathering pump will have to be ascertained, along with the functioning of the pressure-operated cutout switch. This concludes the lesson on propellers.